Allora, ben ritrovati. Procediamo con i lavori. Questa sessione riguarda le stime quantitative di pioggia e di neve, anche se quest'ultima, diciamo, vista la calura che si preannuncia, diciamo, è meno opportuna, e la qualità delle osservazioni radar. Ci saranno 5 contributi. E il primo è del collega e amico Gianfranco Pulpiani, che ci parla di applicazioni tecniche di machine learning per la stima radar della precipitazione. Prego Gianfranco.
Grazie, inizio dalla fine, cioè dal ringraziare i coautori Matteo Guidi ed Emilio Guerriero, senza i quali questo lavoro, che è ancora in una fase preliminare, non sarebbe stato possibile. Allora, rapidamente salto le slide che non sono utili a completare in tempo la presentazione, quindi passo direttamente alla motivazione. Diciamo che il machine learning, più in generale l'intelligenza artificiale, è un trend topic negli ultimi anni, ma in realtà si parla per lo più di tecniche che sono più che maggiorenni. Le prime applicazioni in radar meteorologia, che io sappia, risalgono almeno alla fine degli anni 90 nel campo del nowcasting. Approcci più sistematici per la stima di precipitazione della DSD e quant'altro risale già ai primi degli anni 2000, per cui non mi farei, diciamo così, confondere da questa terminologia. In realtà si tratta di procedure piuttosto consolidate che tuttavia adesso c'è spazio e tempo per poterle rendere davvero operative, anche grazie all'improvement tecnologico riguardante naturalmente la disponibilità di supercalcolo, ma anche e non solo la disponibilità di librerie open source che facilitano decisamente la collaborazione e lo sviluppo di queste metodologie. Da un punto di vista più strettamente di cosa possiamo aspettarci, chiaramente la disponibilità di queste tecniche consente di gestire una grande quantità di dati, ma non solo, di prescindere dalla conoscenza preliminare della dipendenza funzionale tra predittori e variabili target e tra l'altro anche di gestire informazioni non strettamente numeriche per addivenire comunque a stime quantitative di pioggia. Ad esempio possiamo utilizzare etichette o quant'altro, cosa che naturalmente con approcci di regressione tradizionale non è possibile. Evito la slide che ci ho mostrato ieri. Molto rapidamente, le tecniche di machine learning si suddividono in due macroclassi principali, quelle che fanno riferimento all'apprendimento supervisionato, a quello invece all'apprendimento non supervisionato. La differenza sta nel fatto che nel primo caso è nota la variabile target e nel secondo caso no. Nel primo caso le applicazioni più salienti sono quelle che riguardano la classificazione e la regressione, ed è in quest'ultimo ambito che ci muoveremo, utilizzando metodi di ensemble basati sull'utilizzo di alberi decisionali e reti neurali. Dunque, gli ensemble di alberi decisionali, di fatto noi abbiamo focalizzato l'attenzione sulle famose, negli ultimi anni in questo contesto, random forest, e meno noto ma altrettanto performante, se non di più, la famiglia dei gradient boosting, e poi la canonica rete neurale, canonica nella sua architettura multilayer perceptron. Gli alberi decisionali, che sono appunto l'elemento di base degli ensemble di alberi decisionali che abbiamo considerato, di fatto consistono nella suddivisione progressiva del dataset iniziale in più dataset sulla base della verifica di regole decisionali, che consentono quindi di stimare per ciascun sottoinsieme la variabile target, banalmente come media del range di valori assunti in quello specifico intervallo. Le random forest che cosa fanno? Partono da questo semplice algoritmo, l'albero decisionale, e sono costituiti da un insieme di alberi decisionali posti in parallelo, ciascuno dei quali viene addestrato tipicamente su sottoinsiemi del dataset iniziale, determinati attraverso una estrazione random con ripetizione del dataset, in modo tale da avere n dataset che differiscono di poco l'uno rispetto all'altro e che vengono quindi utilizzati per addestrare singolarmente gli alberi. Al termine dell'addestramento e quindi in fase di stima, gli esiti della stima ottenuta da ciascun albero vengono mediati semplicemente. Questa operazione consente di ridurre la varianza Gli alberi decisionali che vengono usati dalle random forest possono essere anche relativamente profondi, si parla in generale anche di strong learners, quindi algoritmi di apprendimento anche profondi, anzi deep learners. Per quanto riguarda invece il gradient boosting, in questo caso invece si tratta di una sequenza, mentre nel primo caso si parlava di alberi decisionali in parallelo, in questo caso si parla di alberi decisionali in sequenza. L'attività svolta dal singolo albero decisionale superiore al primo consiste nel minimizzare i residui derivanti dalla stima fatta nel precedente albero decisionale. Naturalmente, come nel primo caso, la configurazione ottimale si ottiene minimizzando una funzione costo. In che cosa consiste ulteriormente la famiglia dei gradient booster? Si sono evoluti, mentre il random forest è composto da alberi decisionali che possono essere relativamente profondi, generalmente il gradient boosting è composto da alberi decisionali che in realtà sono relativamente poco profondi, si parla appunto di weak learners. L'XG-boost, che sta per Extreme Gradient Boosting, in realtà differisce dal caso generico del gradient boosting per il fatto che gli alberi decisionali possono essere relativamente profondi e soprattutto per il fatto che la funzione obiettivo si compone anche di un termine di regolarizzazione che consente di ridurre i problemi di overfitting. Analogamente per il Light G-boost, e vedremo che la differenza tra questi due approcci è che nel primo caso, quindi l'XG boost, c'è uno sviluppo degli alberi in parallelo, in orizzontale, chiedo scusa, quindi aumenta il numero di nodi decisionali iniziali, mentre nell'altro caso ci può essere uno sviluppo anche prevalentemente verticale. Nel secondo caso sembra essere l'approccio più diciamo, rapido in fase di addestramento e che sfrutta maggiormente la scalabilità delle risorse di calcolo. Reti neurali sono banalmente, volendo trovare una formula, un'espressione matematica, un prodotto matriciale tra una matrice di pesi e bias e una matrice un array di input. I pesi e i bias naturalmente si ottengono attraverso il processo di training, durante il quale appunto, date le variabili input note e target note, si minimizza la funzione costo, e anche qui la funzione costo può essere complessa a piacere in modo da ridurre il problema di overfitting. Allora, venendo a noi, il dataset che abbiamo utilizzato per addestrare e testare questi algoritmi è ottenuto dalle osservazioni della rete radar nazionale. Il periodo di riferimento è luglio 2022 giugno 2023. Sommariamente abbiamo raccolto all'incirca 1 milione di records. Ciascun record è composto da i seguenti predittori, quindi riflettività, tutte le variabili polarimetriche, l'altezza relativa dell'osservazione rispetto allo zero termico, la distanza, l'altezza assoluta, l'attenuazione specifica e l'indice di qualità. La variabile target naturalmente il rain rate, qui parliamo di rain rate, quindi non di precipitazione cumulata, e l'abbiamo ottenuta a partire dalle osservazioni pluviometriche attraverso una procedura di disaggregazione temporale che tiene conto del rapporto tra l'intensità di precipitazione da radar e l'accumulata di precipitazione da radar, quindi lo stesso rapporto è stato utilizzato per appunto procedere alla disaggregazione temporale delle osservazioni pluviometriche. In questa slide, nell'immagine a sinistra, sono riportati gli istogrammi del dataset iniziale a sinistra, di quello filtrato al centro, applicando diciamo, una curva nel piano ZZDR ottenuta da osservazioni da simulazioni, a destra invece un ulteriore filtro e naturalmente filtro dopo filtro c'è una drastica diminuzione del dataset, per cui abbiamo evitato di considerare nello specifico in questa presentazione di focalizzare l'attenzione sui dati ottenuti attraverso l'applicazione del doppio filtro, ma ci limitiamo all'applicazione di un unico filtro, quello appunto nel piano ZZDR, che consente in qualche maniera di ridurre la possibilità di avere dei dati spuri. Nell'immagine a destra abbiamo la distribuzione delle variabili polarimetriche e anche dell'attenuazione specifica stimata attraverso l'applicazione dell'algoritmo ZFI. in termini di box plot o violin plot direi, quindi il primo box plot, quello più a sinistra, rappresenta in decibel il ray rate, che varia quindi fino a circa 300 mm, la riflettività è stata filtrata, c'è un K a 55 dB, riflettività differenziale fino a 4,5 dB, KDP arriva fino a 5 gradi per chilometro, per il fatto che utilizziamo una finestra mobile per la stima molto conservativa, e quindi probabilmente andremo successivamente a ridurla. Attualmente la finestra è di 5 km e questo fa sì che il profilo sia relativamente smutato. E poi abbiamo un'attenuazione specifica che arriva fino a circa 0,8, se non erro, 0,08 dB per chilometro. 3 minuti? Mamma mia. Allora, naturalmente abbiamo fatto un'analisi in componenti principali che ci ha consentito di determinare come le variabili che spiegano almeno il 90% della varianza totale siano la riflettività differenziale, la fase differenziale specifica e il coefficiente di correlazione e attenuazione specifica. I risultati sono mostrati in maniera aggregata, poi in realtà abbiamo fatto anche un'analisi di sensibilità rispetto alla qualità, rispetto alla classe di precipitazione e rispetto al numero di variabili in input. I risultati tra diciamo, la versione standard di gradient boosting e random forest sono piuttosto comparabili, le differenze sono davvero addirittura in questo caso in termini di RMS sulla terza cifra decimale. Rete neurale, almeno nella configurazione che abbiamo utilizzato, abbiamo ricavato dalla minimizzazione e dall'ottimizzazione delle varie reti configurazioni possibili, ci portano a differenze invece comunque sulla prima cifra decimale, quindi diciamo, continuiamo a ritenere che siano piuttosto consistenti tra loro. C'è un ulteriore miglioramento attraverso l'applicazione dell'XGBoost, sempre però di ordine inferiore. Naturalmente, se paragonate agli algoritmi parametrici tradizionali, parliamo di Marshall-Palmer piuttosto che Yost-Vogel, piuttosto che loro combinazioni con algoritmi che usano l'HDP, le differenze in termini percentuali possono anche raggiungere il 20%. Questa slide riassuntiva semplicemente riporta la classifica, per così dire, sebbene come ho anticipato le differenze siano davvero trascurabili, tra l'XGBoost, Random Forest, Gradient Boosting e infine le reti neurali. Tuttavia, utilizzando diciamo, una rappresentazione diciamo, proposta da Emilio Guerriero, Mimmo, recentemente, che si è inventato diciamo, di questa rappresentazione in un piano che non è il canonico performance diagram, ma è un efficiency diagram. Di fatto rappresenta nel piano sull'asse verticale c'è il bias, sull'asse orizzontale c'è l'RMSE. L'efficienza di fatto è definita come 1 meno la distorsione, dove la distorsione non è altro che una combinazione del bias e dell'RMSE. Quindi l'ideale è avere i punti sull'asse orizzontale per avere un bias nullo e quanto più possibile vicino all'origine per avere appunto un RMSE contenuto. In questa rappresentazione si vede appunto come ci sia l'XGBoost, gli algoritmi sono denominati attraverso le prime due lettere, quindi XGBoost attraverso acronimi, XGBoost e RF sono molto vicini, sebbene appunto ci sia una performance migliore dell'XGBoost, mentre è leggermente distanziata dalla rete neurale. Naturalmente il Marshall-Palmer per esempio, ma così vale anche per gli altri algoritmi parametrici, sono peggiori sia in termini di bias che soprattutto di RMSE e per quanto riguarda l'RMSE c'è da dire che l'errore medio è relativamente basso, prossimo allo zero per gli algoritmi di machine learning, per cui gran parte dell'errore è da attribuire alla direzione standard. In questa slide invece che cosa abbiamo provato a fare? A studiare la sensibilità della performance dei diversi algoritmi in funzione del radar utilizzato. Ad oggi sembrerebbe che tra i migliori radar disponibili su piazza in Italia ci sia il nuovo radar di Fossalon e si nota come passando dal radar 1, Fossalon, al radar 2, al radar 3, quindi Armid e Serrano, ci sia un peggioramento anche molto marcato della performance, e questo in qualche maniera naturalmente ci fa nulla di particolarmente innovativo, se non il fatto che appunto ci fa capire quale sia l'importanza della qualità dei dati, anche naturalmente nel contesto operativo nel quale ci si trova ad operare, ma ci sono differenze molto importanti, ad esempio, tra Fossalone e Montesirano in termini di MSE. Questa slide invece riporta la matrice di confusione per l'XG boost sulla sinistra e per la rete neurale sulla destra, un po' gli estremi delle tecniche di machine learning che abbiamo considerato, e si nota come la performance migliorino all'aumentare l'intensità di precipitazione in entrambi i casi. Rapidamente queste slide in realtà sono state ottenute con un dataset che non è aggiornatissimo rispetto a quello mostrato in precedenza, ma non abbiamo completato l'analisi, e semplicemente l'obiettivo era quello di mostrare la sensibilità rispetto al numero di input e quindi alla diminuzione della varianza spiegata dalle variabili, e si nota come naturalmente c'è un effetto, se non drammatico, e la cosa interessante è che in realtà in questa analisi preliminare si è visto come fosse la rete neurale l'algoritmo meno sensibile alla diminuzione del numero di input e quindi alla diminuzione della varianza spiegata. Per concludere quindi in questo lavoro che stiamo per completare abbiamo analizzato e confrontato una serie di algoritmi di machine learning di base ensemble decision trees, in particolar modo random forest, gradient boosting e variazioni di quest'ultimo, reti neurali. Sostanzialmente quello che abbiamo trovato è che le performance sono davvero comparabili. Naturalmente quello che non ho detto in precedenza è che le random forest si possono addestrare in maniera molto più agevole rispetto agli altri algoritmi. Tuttavia ritengo che ci sia ampio margine di miglioramento soprattutto per le reti neurali, e quindi questa sarà la prossima attività, quella di verificare eventualmente anche ensemble di reti neurali, e qui decisamente mi aspetto un miglioramento. Per cui abbiamo visto anche che c'è una sensibilità rispetto alla qualità dei dati e cos'altro. Rispetto alle tecniche tradizionali naturalmente, ma questo già lo sapevamo, c'è un improvement almeno del 15-20%. Avrei concluso.
Grazie Gianfranco, probabilmente hai fatto diventare qualche weak learner un improved learner. Una domanda rapida, se c'è di giù.
Molto interessante. Una domanda però. Immagino che ti sarai scontrato con il fatto che il dataset sia molto sbilanciato verso intensità di precipitazioni molto basse. Come avete fatto poi a convincere questi algoritmi che effettivamente non esiste soltanto l'intensità di precipitazione tendente a zero, ma anche istruirli al fatto che esistono precipitazioni più intense?
Grazie. Allora, i risultati generali aggregati sono stati ottenuti semplicemente lavorando sull'intero dataset, ed è i risultati che ho mostrato si riferiscono a quello, quindi non abbiamo fatto addestrato in maniera separata il dataset. Lo abbiamo fatto soltanto in questo caso per vedere la sensibilità della performance rispetto alle diverse classi di precipitazione. Classi di precipitazione che sono state individuate dividendo in maniera uniforme dal punto di vista della capienza, diciamo, della numerosità in tre classi, quindi la classe di precipitazione bassa da 0 a 3,9 mm, la seconda da 3,9 a 7 mm e la terza da 7 mm in poi, quindi ciascuno contiene il 33% della distribuzione complessiva. E in questo caso, come dicevo, abbiamo visto che addirittura ci può essere un miglioramento andando verso classi di precipitazione più alta, ecco. Però a parte questo studio di sensibilità non abbiamo nei risultati aggregati insegnato specificatamente a riconoscere l'uno o l'altro.
Grazie Gianfranco. Passiamo rapidamente alla seconda presentazione che parla di combinazioni di misure radar e pluviometri, quindi rappresentata da Rossano Ciampalini. Prego, Rossano.
Sì, buongiorno a tutti, Rossano Ciampalini, Università di Firenze. Torniamo un po' alle origini come elaborazione, perché presento qui una combinazione di misure radar pluviometriche con differenti metodologie che intendiamo applicare o stiamo applicando sulla regione per la modellistica idrologica. Intanto diciamo che per quanto riguarda la registrazione radar meteo è un supporto imprescindibile per la modellistica dei processi idrologici e quindi nel nostro caso, specialmente nel caso della modellistica idraulica e idrologica e degli eventi estremi. A causa delle sorgenti di errore a cui tale misura è soggetta, quella radar appunto per la previsione meteorologica, la qualità dei dati necessita di essere migliorata con correzioni basate su osservazioni pluviometriche e quindi c'è tutto un discorso piuttosto ampio con una vasta letteratura in merito. Qui ho messo giusto una review che tratta alcuni casi, però ecco, il merging del dato pluviometrico e radar è una cosa molto analizzata, molto studiata. Quindi facciamo adesso un passo indietro per vedere su quale contesto applichiamo queste metodologie. Il contesto è quello di un progetto, il progetto SEDRAN dell'Horizon 2020, il Soil Erosion Under Extreme Rainfall Events, Detecting and Modeling Using Radar Runoff Nowcasting System. Praticamente è un fellowship MSCA dell'Horizon 2020, dove l'obiettivo è quantificare l'effetto di forti piogge sull'erosione del suolo, utilizzando appunto dati radar e osservazioni pluviometriche, modellando l'erosione del suolo e il runoff a scala regionale. L'alto valore di questo lavoro dovrebbe essere la scala spaziale e temporale ad alta definizione con un follow-up dinamico degli eventi, comunque abbastanza innovativo per quanto riguarda l'erosione del suolo, perlomeno in Italia e anche in Europa. Quindi diciamo che gli istituti di ricerca interessati di cui non ho parlato sono il Dipartimento di Scienze della Terra di Firenze e il Consorzio LAMMA appunto di Firenze della regione toscana. Sempre restando un po' sul contesto, ricordare, perché ci agganciamo a questo discorso del radar, gli eventi piovosi intensi impattano in modo significativo sul riscellamento, sugli eventi di piena, sull'erosione del suolo, cosa che ci riguarda, e la dimensione spazio-temporale dei processi di erosione è di grande rilevanza, confermato da moltissimi studi, insomma, questa è cosa consolidata. Quindi per apprezzare tali effetti su eventi, su pulsazioni locali, come le chiamiamo su scala di bacino e sottobacino, per noi occorre focalizzare su dati pluviometrici a scala chilometrica o subchilometrica su scala temporale, suborare, quindi si va sui minuti e quindi torna al discorso del radar. Questo per poi lavorare in particolare attraverso la modellazione delle piogge al suolo rispetto all'evoluzione delle celle di alta intensità specifica da dati radar, ma questo sarà il seguito del lavoro che comporta appunto la simulazione a livello regionale. Per fare tutto questo noi abbiamo qui, cerchiamo un'integrazione delle piogge radar e misure pluviometriche a scala regionale. Quindi questo lavoro tratta in maniera preliminare un confronto tra tre diverse procedure di combinazione di dati radar e pluviometrici sempre sulla regione, con dati suborari e giornalieri di un numero selezionato di eventi di pioggia, con i metodi che ora vediamo rapidamente, che sono il kriging con external drift, il probability matching method e l'adjusted conditional merging con i dati fornitici dall'elaborazione appunto della protezione civile che fornisce l'SRI Adjusted in questo senso. Questi metodi si basano su precipitazioni registrate da pluviometri con frame di 15 minuti su 800 stazioni circa nella regione, qui a sinistra la posizione dei pluviometri, e delle immagini di riflettività K, sempre fornite dal DPCM, Constant Altitude Plane Position Indicator, con la riflettività di BZ, alle volte 2000, 3000 e 5000, in particolare sulla 3000 dopo si lavorerà, con tempo di campionamento a 10 minuti. Questi sono i dati che utilizziamo per fare questo confronto, prima per ricavare il dato e poi per fare il confronto. Tornando ai metodi, velocissimamente, si diceva appunto il Kriging External Drift KED, dati osservati da pluviometri con Kriging in prevalenza di trend spaziale, rappresentato dalla riflettività radar qui, il Probability Matching Method, che mette in relazione coppie di riflettività radar K non sincrone e di intensità di pioggia nei problemi attraverso una relazione ZR attraverso due distribuzioni cumulate, cumulative distribution function, quindi c'è un matching tra le due distribuzioni cumulate, e l'adjusted fornito dalla protezione civile che utilizza un Kriging ordinario per i dati osservati con le differenze relative osservate nel campo della gravità radar, che vengono anche queste dopo un crigaggio aggiunte al modello perché è appunto un adjusted conditional merging. Questi sono i tre metodi che abbiamo utilizzato. Quello della protezione civile ci viene fornito ovviamente già elaborato. Il confronto di questi tre dati semplicemente è un'analisi preliminare appunto dei rainfall fields a 30 minuti e giornaliero, che a questo punto l'abbiamo fatto sia con un confronto diretto dei pattern visuale e poi con un'analisi della varianza con coefficienti esplicativi sulle differenze tra un metodo e l'altro, residui di cui abbiamo ricavato vari parametri, bias, RMSE, median absolute deviation, coefficiente di indexing di Kolmogorov-Smirnov e un confronto delle cumulative distribution function relative. Quindi abbiamo questi tre metodi di cui abbiamo la differenza, ai quali applichiamo questi indicatori per valutare la discrepanza tra un metodo e l'altro. In quanto non abbiamo uno zero assoluto, abbiamo il zero dei pluviometri, però i pluviometri sono utilizzati in tutti i metodi, quindi ci sarà una valutazione con un leave one out su due di questi metodi, però come zero dobbiamo limitarci a questo, quindi fare questa valutazione, però il confronto è diretto in questo senso. Quindi velocemente andiamo su un confronto visuale. Allora, qui abbiamo scelto le piogge su alcuni giorni, abbiamo 4 casi studio. A sinistra abbiamo le elaborazioni per quanto riguarda il giornaliero sulla regione e qui a destra l'interpolato delle precipitazioni sui pluviometri per avere un confronto visuale, per capire intanto alcune cose. Facciamo uno zoom su 2 di questi eventi. Gli eventi erano il 1° aprile 2022, il 2 aprile, il 18 agosto 2022, non so se vi ricordate quel temporale passaggio estivo, e il 10 novembre 2022. Allora, se andiamo sul giorno del 1° aprile, allora, qui a sinistra abbiamo in ordine i dati K immediati sulla giornata, questo in alto, poi l'SD adjusted fornitoci dal DPCN, l'applicazione del Kriging con external drift qui in fondo a sinistra e il probability matching method qua. Con un confronto piuttosto rapido visuale, intanto si individuano dei piccoli problemi che riguardano le zone d'ombra radar non risolte che derivano dal CAPI, che sono qua, non risolte dall'adjusted, che sono qua, e non risolte dal PMM. Tutta questa zona in ombra qua tutta questa zona scura, sono zone in ombra radar per quanto riguarda la regione e che sono là. In realtà è ancora più vasta la zona perché va più in basso. Poi ci sono altri dati radar anomali, per esempio qua l'effetto stella con eco radar indesiderati, questo sull'Appennino, anzi qui è la somma sia di un effetto ombra sia di un effetto eco, che ci dà altri problemi. Ora, se vi ricordate il grafico degli errori fattoci vedere ieri da Protezione Civile, questo riflette ampiamente la bontà del dato per quanto riguarda la Toscana. Per noi è un problema perché in questo caso si tratta di migliaia di chilometri quadrati e sulla mappa di ieri il giallo e il rosso corrispondeva al 40-50% della regione, quindi abbiamo questo piccolo problemino. Sull'evento un po' più forte che è quello del 18-8 abbiamo cose simili, vediamo sempre zone in ombra qua dalla parte centrale della regione, anche qua rispetto a quella interpolata con il W dei pluviometri, e da tutte e due risulta alla fine che quella interpolata con il Kriging con external drift esce da questo problema, perché l'elemento lettura, osservazione pluviometro riesce in qualche maniera nella minimizzazione dell'errore tra i due parametri a compensare questo fatto della zona d'ombra. Quindi per quanto ci riguarda in questo momento, almeno in questo caso, la cosa viene risolta da questo. Abbiamo fatto poi un confronto sulle serie giornaliere delle differenze tra i tre metodi, KD, PMM, KD adjusted, PMM adjusted, sull'RMSE, quindi per ogni step di mezz'ora abbiamo calcolato le differenze e calcolato l'RMSE per vedere l'andamento della serie in questo confronto, insomma, tra queste metodologie. Ora, velocissimamente, le cose che si possono osservare sono, allora, qui avete in questo plot le varie differenze, KD PMM, KD adjusted, PPM adjusted e la pioggia accumulata, che è questa linea qua. Abbiamo che intanto ci sono dei picchi dove abbiamo più pioggia, ma quello è piuttosto normale perché essendo maggiore l'estensione del segnale, anche l'errore, se c'è, risulta maggiore, quindi quello poi ci sarà una valutazione dell'errore relativo in futuro. Poi possiamo dire sulle medie che qui siamo in questo caso qua, qui ci sono le medie. Le medie sull'RMS sono molto simili, sono un po' più alte per quanto riguarda il KE adjusted e il PMM adjusted nei confronti, quindi poi viene in mente che ci sia qualcosa di sistematico tra come viene utilizzato il dato in adjusted e nel nostro approccio, che probabilmente non so, comunque sono molto limitate le differenze. Per quanto riguarda il bias, sì, sono in fondo. Per quanto riguarda il bias, abbiamo un bias leggermente negativo per quanto riguarda il probability match method contro l'adjusted. Questo è probabilmente dovuto alla sottostima delle piogge che il probability match method ci dà, perché non riesce a elevare bene i picchi, mentre il KID PMM, che è qua, ci influenza nelle forzature in alto, ha un bias leggermente positivo perché la lettura sul pluviometro probabilmente dà più importanza all'interpolazione. Queste sono le idee che ci sono venute in questo senso. Stesse valutazioni si fanno sulla pioggia intensa del 18-8. L'unica differenza forse può essere nell'RMSE tra i metodi PPM adjusted, dove la forte influenza del radar dei due metodi, avendo un forte contributo, riduce un po' i valori dell'errore. Però ecco, stesse considerazioni si fanno per quanto riguarda il bias che si è visto poco fa. Questo è, siamo appena qua, quindi a questo punto abbiamo soltanto che si può dire le elaborazioni producono ricostruzioni spaziali diverse a seconda della procedura applicata, più vicine alla variabilità radar quando si utilizzano il PMM e l'adjusted, più correlate alla struttura dei dati pluviometrici con il KID, con il Kriging, con external drift. La metodologia adjusted più channel non mostra un effetto di limite superiore, perché è più complessa e perché c'è una Marshall pattern con un'addizione dei valori vengono dal radar. Questo problema invece è presente nel PMM. C'è una risposta diversa della performance in base alla tipologia di pioggia dovuta all'interazione con il radar, da valutare nella scelta dei vantaggi e negli svantaggi relativi. C'è da dire poi che i metodi di confronto producono risultati non univoci per adesso e necessitano ulteriori investigazioni. Infatti, se non si va negli sviluppi futuri, sappiamo che diverse cose ci restano da fare, ovvero l'applicazione ad un numero rappresentativo di eventi con serie annuali per individuare trend significativi, concludere quella che stiamo facendo, la valutazione dei metodi applicati KD e PMM con una validazione live on out, per dare un valore numerico a quello che stiamo facendo, un'analisi dell'errore a diverse scale temporali, 1 ora, 3 ore, eccetera, per vedere l'andamento delle nostre stime prendendo intervalli temporali diversi. Grazie dell'attenzione.
Grazie a te. In tempismo perfetto, domande? Io ne ho una rapidissima. Avete provato a fare per valutare, diciamo, le performance dei vari metodi, aspetti di cross validazione, cioè tenersi dei pluviometri solo per la validazione, quindi non farli entrare nelle tecniche che ci hai illustrato?
Sì, no, ma lo stiamo facendo perché il live on out che si può fare è quello, e l'unico dubbio era quanti pluviometri togliere, perché anche lì conta la distanza dei pluviometri, che sono punti a decine di chilometri, e quindi quello lo stiamo facendo, è un punto da
Ottimo.
studiare.
Grazie mille. Passiamo velocemente alla prossima presentazione, che ci introduce invece aspetti sulla qualità del radar in termini di rimozione di echi interferenziali. A presentarla è Chiara Cardinali. Prego Chiara.
Grazie. Buongiorno a tutti. Questa presentazione riguarda il lavoro che è stato svolto nell'area radar di ARPA Emilia-Romagna per individuare un metodo per la caratterizzazione e la rimozione efficace degli echi interferenziali nei volumi radar di ARPA Emilia-Romagna. Infatti nel corso degli ultimi anni il numero di occorrenze dell'interferenza associata a Wi-Fi nel composito regionale è aumentata fortemente, quindi è nata l'esigenza appunto di trovare un metodo efficace per rimuovere questi echi non meteo. E quindi è stato proposto un algoritmo, è stato poi testato sui volumi radar di ARPA Emilia-Romagna, basato su tecniche di logica fuzzy. Questo algoritmo di base prende ogni cella del volume radar e la classifica in 5 possibili categorie di eco, scelte tra gli echi associati il segnale associato a eco meteo, clutter, interferenze multiple, medie e deboli, e sceglie la classe che ritiene più probabile, utilizzando le funzioni trapezoidali tipiche della logica fuzzy. Per costruire il framework necessario per poter applicare la logica fuzzy è stato realizzato per ciascuno dei 2 sistemi radar in gestione ad ARPA Emilia-Romagna un dataset di settori di volumi radar, dove questi volumi sono stati scelti scenari meteorologici differenti e i settori sono stati estratti in modo che alla prima elevazione, PPA è la prima elevazione del volume radar, contenessero in modo esclusivo il segnale associato ad una delle 5 classi di eco che abbiamo considerato. Questa estrazione è stata fatta manualmente con un metodo di riconoscimento visivo da parte del radarista. Poi su ciascun dataset, quindi per ciascun sistema radar, è stata eseguita un'analisi statistica in modo da realizzare le distribuzioni delle grandezze radar archiviate nei volumi radar e quindi individuare le distribuzioni per queste grandezze per ciascuna classe di eco, e così sono stati individuati gli intervalli dei valori probabili e i parametri da usare nella logica fuzzy, in quanto appunto andiamo a calcolare le probabilità delle classi di eco utilizzando delle funzioni trapezoidali. Come vediamo nel box in basso a destra, la probabilità che il segnale S in una cella radar appartenga alla classe CK, dato il valore di una grandezza radar X in quella cella, si può appunto ottenere con la funzione trapezoidale rappresentata in questo box, e che dipende quindi da 4 parametri, x1, x2, x3, x4, che sono i vertici del trapezoide. E nel caso di più grandezze radar disponibili, appunto la probabilità della classe si ottiene come la somma pesata delle probabilità condizionate al valore delle grandezze disponibili. E questi parametri vengono scelti appunto tenendo conto delle distribuzioni che abbiamo ottenuto sui campioni raccolti. Questo è l'elenco delle grandezze radar utilizzate, in particolare il Signal Quality Index non è disponibile per il radar di Gattatico, ma solo per il radar di San Pietro Capofiume, e quella che chiamiamo ZVD è è calcolata come la differenza sulla verticale tra l'elevazione superiore e l'elevazione inferiore di riflettività, calcolata tutte le elevazioni esclusa l'ultima. A titolo di esempio riportiamo le distribuzioni ottenute per i campioni raccolti, in alto per San Pietro Capofiume e in basso per il radar di Gattatico, a sinistra per la ZDR, a destra per la texture di ZDR, in colori diversi per le varie classi di eco considerate. In particolare le distribuzioni in blu sono quelle per la classe degli echi meteo, e vediamo che la distribuzione degli echi meteo per i campioni raccolti per entrambi i due sistemi radar della texture di ZDR è abbastanza discosta rispetto alle distribuzioni delle altre classi di eco, quindi è una grandezza che ci permette una buona discriminazione tra i segnali associati agli echi meteorologici e gli altri tipi di sorgenti, a differenza invece della ZDR in cui le distribuzioni delle varie classi di eco sono sovrapposte nonostante la forma sia differente e dunque i valori sono possibili per le varie classi di eco, gli stessi valori. In particolare, quindi, ad esempio, la probabilità condizionata al valore della texture di ZDR avrà un peso maggiore nella somma pesata che abbiamo visto prima. E, inoltre possiamo vedere che le distribuzioni ottenute per il campione raccolto per il radar di Gattatico per la ZDR ad esempio sono molto più rumorose rispetto a San Pietro Capofiume. Questa differenza si può spiegare anche con il fatto che si tratta di un sistema di tipo diverso, infatti a San Pietro Capofiume la trasmissione è onda continua, mentre a Gattatico è alternata. Quindi a seconda del sistema radar, avendo sistemi radar diversi, le distribuzioni sono diverse, i parametri da ottimizzare per la logica fuzzy devono appunto essere ottimizzati in modo indipendente per i due sistemi radar. Inoltre è stata modificata l'implementazione della funzione trapezoidale con cui vengono calcolate le probabilità di classificazione in modo da tener conto il caso di distribuzioni non gaussiane e in generale nello specifico è stato introdotto un parametro opzionale che chiamiamo X5 soprattutto per tenere conto delle grandezze che presentano un alto numero di occorrenze di undetect per il campione raccolto. E nel caso in cui le grandezze ammettono valori probabili su intervalli disgiunti, come nel grafico in alto a sinistra, si prende il massimo tra la funzione trapezoidale applicata ai due intervalli. Quindi complessivamente è stato ottimizzato un gran numero di parametri e pesi in modo indipendente per ciascun sistema radar. I risultati però ci sono sembrati soddisfacenti e presentiamo alcuni esempi delle ripuliture ottenute per i due sistemi. In particolare vengono messi a confronto i PPI alla prima elevazione a sinistra del volume originale non ripulito, al centro del volume ripulito con l'algoritmo precedentemente operativo ad ARPA Emilia-Romagna, che è basato su un albero decisionale che però non tiene conto delle grandezze polarimetriche disponibili, e infine a destra quello ripulito con l'algoritmo di fuzzy logic sviluppato con la configurazione ottimizzata per San Pietro Capofiume, perché questo è un esempio per San Pietro. Vediamo che appunto in quest'ultima versione c'è una buona rimozione delle interferenze e del rumore e una certa tendenza a rimuovere eccessivamente il segnale, soprattutto quello più debole, associati ai sistemi all'ecometeo. E in particolare in questo secondo esempio vediamo che c'è una rimozione efficace delle interferenze che però ha il difetto di rimuovere eccessivamente segnale creando dei buchi sulle strutture di precipitazione e vedremo che comunque si può minimizzare questo problema. In questo esempio per Gattatico invece oltre ad una buona rimozione dell'interferenza e del rumore, migliore rispetto all'algoritmo dell'albero decisionale, c'è anche una migliore capacità di riprodurre le strutture di precipitazione. Tuttavia si può vedere guardando nel settore a sud-ovest rispetto al sito radar che l'eco nella direzione dei crinali appenninici non è stato ben rimosso. In particolare, se andiamo a zoomare in questo settore, vediamo la differenza tra le due versioni di ripulitura e che l'algoritmo di fuzzy logic è stato meno efficiente rispetto all'albero decisionale e vengono presentati i valori di riflettività, se ci spostiamo sulla sinistra della slide, alla prima elevazione e alla seconda, e vediamo che alla prima elevazione si tratta di un caso particolare in cui alla prima elevazione abbiamo il beam blocking, partial beam blocking, mentre alla seconda elevazione c'è un eco di ritorno associato a clutter, in quanto il segnale radar intercetta i crinali appenninici che sono presenti appunto in questa zona. E di conseguenza, ad esempio, se ci concentriamo su questo settore con i valori della differenza di riflettività tra la seconda e la prima elevazione, vediamo che sono possibili, in particolare ci sono valori altamente positivi che sono probabili anche e soprattutto per gli echi meteo. Quindi è un caso particolare in cui valori degli echi non meteo cadono negli intervalli di valori probabili per gli echi meteo e quindi non riusciamo bene a discriminare nonostante le ottimizzazioni. Per quanto riguarda invece il problema dell'eccessiva rimozione di eco meteo, si è visto che questo problema si può minimizzare introducendo delle condizioni di forzatura, andando quindi a forzare alla classe meteo quelle celle radar in cui la differenza tra la probabilità della classe assegnata dall'algoritmo, che l'algoritmo ritiene più probabile, e la probabilità della classe meteo è assunta piccola, e le soglie da utilizzare per queste condizioni di forzatura sono state scelte con un ulteriore processo di ottimizzazione in modo indipendente per i due sistemi radar. Questo ultimo esempio ci mette in evidenza l'importanza delle condizioni di forzatura e in particolare se ci concentriamo sul PPI a destra, quello ottenuto dal volume ripulito con l'algoritmo di fuzzy logic nella configurazione ottimizzata sia in termini di pesi che di parametri trapezoidali che di condizioni di forzatura, e lo confrontiamo con la stessa versione ma con le condizioni di forzatura disattivate, vediamo che la maggior parte del segnale in questo secondo caso è persa, mentre nel primo caso si ha un buon risultato. Infine presentiamo brevemente i risultati della verifica su un solo caso studio delle cumulate orarie da radar rispetto alle cumulate pluviometriche, confrontando gli effetti delle due versioni di ripulitura. In particolare indichiamo con master la versione ottenuta utilizzando come algoritmo di ripulitura l'albero decisionale e updating quello basato su fuzzy logic sviluppato. Quindi l'evento va dal 15 al 18 settembre 2022 e come vediamo nel box a destra, il mean absolute error è migliore per updating. Al centro della slide invece sono riportati gli andamenti degli score dicotomici su tutto l'evento e al variare della soglia. Vediamo che si nota subito un forte scarto in termini di bias tra le due versioni, con una miglior performance per la versione updating, quindi quella basata sulla ripulitura con la fuzzy logic, che è maggiormente evidente alle soglie più alte. Invece il pod è più basso, ad esempio, possiamo vedere, soprattutto alle soglie alte per l'updating, e questo è coerente col fatto che la versione di fuzzy logic per la ripulitura tende a rimuovere eccessivamente il segnale meteo e anche a penalizzare i picchi di precipitazione. Mostriamo anche due esempi per due istanti di questo evento delle mappe del composito ottenute. A destra vediamo la versione updating, a sinistra la versione master, e notiamo appunto che nella versione updating sono rimosse bene le interferenze e le strutture di precipitazione sono riprodotte abbastanza bene. Inoltre, soprattutto come si può vedere nel secondo caso, anche il rumore è notevolmente ridotto, ma se ci focalizziamo ad esempio qui, vediamo che il picco è penalizzato nella versione updating, anche se leggermente. E poi abbiamo infine un esempio di mappa di cumulata oraria, sempre updating a destra e a sinistra la versione master, e sotto sono sovrapposti i pluviometri, quelli che hanno registrato una cumulata maggiore di 0 in questa fascia oraria, e vediamo che i campi sono consistenti. La differenza sta nel fatto che in updating viene rimossa il contributo dovuto alle interferenze che invece rimanevano nei compositi della versione master. Concludendo, quindi il metodo di logica fuzzy sviluppato permette di rimuovere abbastanza bene interferenze e rumore e di riprodurre abbastanza bene le strutture di precipitazione, quindi complessivamente possiamo dire che la qualità delle osservazioni radar e dei prodotti di cumulata è migliorata. Tuttavia comunque l'algoritmo non è generalizzabile, perché il processo di ottimizzazione deve essere ripetuto in modo indipendente per ogni sistema e il numero dei parametri da ottimizzare è abbastanza alto. C'è anche questo problema di un un'eccessiva tendenza a rimuovere l'ecometeo, che comunque si può minimizzare con le condizioni di forzatura, come abbiamo visto, e soprattutto con un successivo post-processing, perché appunto le mappe di ZLR e poi dei compositi si ottengono su diversi step. Grazie dell'attenzione.
Grazie a te Chiara. Domande? Innanzitutto ringraziamo anche il radarista che ti ha supportato nel classificare manualmente gli echi, gli echi interferenziali. Sarebbe interessante avere anche disponibile questo dataset, perché si presta a tecniche differenti rispetto alla FASI, quindi sembra una buona cosa. Una domanda, avete quantificato quant'è la rimozione eccessiva? Se è quantificabile poi.
No, diciamo...
Giusto per dare un numero, no? Miglioriamo del X%. Va bene, allora è un suggerimento il mio, più che una domanda.
Grazie.
Allora, passiamo all'ultima presentazione, dal titolo Radar polarimetria di un evento di SHAF sul bacino del Po di Antioco Vargiu, che ha l'onere di separarci dalla pranzo / tavola rotonda, quindi...
Buongiorno a tutti, spero di essere veloce, quindi è Antioco Vargiu, ARPA Lombardia. Vi introdurrò un evento abbastanza curioso che ci è capitato sulla testa. Siamo, come ha detto stamattina Orietta, abbastanza giovani. Diciamo che questo evento è stato abbastanza curioso e per questo abbiamo deciso anche di portarlo in questo contesto, anche per farvi vedere un po' qualche risultato. Ovviamente grazie alla polarimetria questo evento si è potuto classificare correttamente, anche se all'inizio diciamo, ha creato un po' di scompiglio. Vi faccio vedere come prima slide ovviamente la rete radar dell'ARPA Lombardia. Ve ne ha parlato stamattina Orietta, semplicemente rimando che se parlo del radar di Desio intendo una località vicina a Milano, se parlo del radar di Flero una località vicino a Brescia. Quindi come sarà sviluppata velocemente, cerco di essere abbastanza veloce, quindi faccio una piccola introduzione del chaff effect, che anche noi ce lo siamo dovuti studiare perché effettivamente ci ha lasciato un po' perplessi, e poi descriverò la situazione partendo dalla situazione meteo di quel giorno particolare e poi come è stato visto da diversi radar, tra cui il radar il composito di Meteo Svizzera, il composito nazionale e poi anche quello, diciamo, le variabili viste dalla nostra rete, in particolare riflettività massima come sostanzialmente rilevatore e poi le variabili polarimetriche che in qualche modo hanno discriminato l'evento. Ovviamente con anche ripercussioni nella discriminazione idroclasse. Un pochettino mi rifaccio all'ultima presentazione in cui l'algoritmo utilizzato per la idroclasse è un algoritmo fasi che sviluppato dalla Vaisala. Noi abbiamo preso l'algoritmo, non abbiamo ancora avuto modo ovviamente di mettere le mani in noi, però la Vaisala aveva validato anche dei casi di chaff, quindi curiosamente questo evento è stato in qualche modo discriminato. E poi ovviamente l'altra cosa curiosa e interessante è che questo caso di chaff può essere utilizzato anche come tracciante di flusso, e in particolare per quell'evento c'erano delle condizioni meteo abbastanza significative, non da un punto di vista meteorologico, non, diciamo di allerte, non c'era niente di particolare, però interessanti. Allora, intanto incomincio subito velocemente col chaff effect. Il chaff è una contromisura militare, cioè sostanzialmente sono dei mazzi di, chiamiamole pagliuzze, della grandezza sostanzialmente sono fini più o meno come i nostri capelli o leggermente più fini, e hanno una dimensione, una lunghezza variabile che deve ottimizzare lo scattering con varie frequenze dei radar, ovviamente dei radar che devono osservare un oggetto che si avvicina. Quindi è utilizzato in campo militare. Abbiamo questi mazzi, vengono espulsi a una certa quota, se stiamo parlando di una contromisura per quanto riguarda aerea, e sono milioni di fibre. Diciamo che devono avere una caratteristica di persistere in aria abbastanza sufficiente per far scappare chi ha emesso queste fibre, e oltretutto ha una caratteristica che dopo un paio di secondi queste fibre si posizionano in una sorta di dimensione più orizzontale che verticale e cadono lentamente con un moto di avvitamento, e quindi anche questa è una caratteristica che poi i radar possono osservare. La domanda è ovviamente che ci siamo posti: ma è dannoso questa nuvola qua, queste pagliuzze sono dannose per l'uomo? No, nel senso che non le respiriamo perché sono sufficientemente grandi, però ovviamente un accumulo di questi oggetti, ho dimenticato di dire che sono sostanzialmente riflettenti elettromagnetici, quindi sono di alluminio o un altro metallo, comunque possono accumularsi e quindi in ogni caso sono degli agenti esterni dove cadono. Quindi, fatta questa doverosa premessa, vado ad analizzare velocemente la giornata che era il 1° febbraio di quest'anno. Da un punto di vista meteorologico vediamo che l'Europa è dominata da un bel dipolo con una bassa pressione sull'Europa orientale sino alla Scandinavia, e una zona di alta pressione sull'Atlantico, e poi sull'Europa centrale un bel gradiente di geopotenziale che sostanzialmente ha determinato dei venti e anche un jet stream abbastanza importante, e lo vediamo, questo è il Sound di Novara Cameri, con velocità del vento che progressivamente con la quota si sono portate anche oltre 100 km all'ora ad altezze dell'ordine di 7.000 metri. Quindi da un punto di vista meteorologico sulla regione non c'erano grosse criticità. Vedete la mappa della nuvolosità, praticamente flussi asciutti, rinforzi di vento in quota, nessuna criticità sostanzialmente al suolo. Ma quello che è successo è che a un certo punto abbiamo incominciato a vedere un eco strano sui nostri radar, meglio dire non solo sui nostri ma sui principali radar come vi ho accennato. Quindi qua vi mostro una sequenza temporale che parte circa dalle 9:15 e finisce alle 3 del pomeriggio, dove traccio prima con radar Meteo Svizzera, poi con la massima riflettività del nostro sistema, e poi con il sistema nazionale questo evento. Vediamo che sostanzialmente la precipitazione equivalente è abbastanza bassa, però rilevabile, e quindi questo ci ha creato qualche problema. Cosa sta succedendo? Dalla Svizzera che cosa sta succedendo? Esperimenti strani, il CERN ha prodotto un buco nero, ci siamo un pochettino confrontati, tra le varie ipotesi c'è stato anche qualcuno, ma sarà forse CHAF, non CHAF, boh. E fortunatamente, grazie anche a un dialogo che c'era con ARPA Piemonte, quindi abbiamo contattato Renzo, e Renzo ci ha detto: no, attenzione, guardate che i militari svizzeri stavano facendo un'esercitazione di CHAF, senza però, come possiamo dire, dare diffusione e importanza di questo avvenimento. Quindi sostanzialmente quello che abbiamo visto è che l'evento è iniziato nelle regioni centrali della Svizzera, intorno tra le 8:30 e le 10 UTC, e poi si è propagato con questo flusso nord-occidentale abbastanza vigoroso per le Alpi svizzere, poi ha passato il confine, è entrato nella giurisdizione italiana ed è proseguito. Qua vi faccio vedere la traccia rilevata, sarebbe tra virgolette la precipitazione cumulata durante l'evento, che è di poco, dell'ordine di mezzo millimetro, con qualche punto di accumulazione un po' più forte. Questa è la traccia del nostro radar, e poi c'è un punto in cui probabilmente l'interazione tra il CHAF e l'orografia è maggiore, e anche un punto in cui i nostri radar, probabilmente anche quelli di Meteo Svizzera, hanno una visibilità un po' peggiore. Però è interessante perché anche questo punto può avere qualche effetto in tutto l'evento. Questo invece è quello che è stato visto dal composito nazionale, e si vede che il fine evento è stato rilevato nell'Adriatico presso Ravenna. Quindi in totale un evento che ha come dimensioni macroscopiche, stiamo parlando di qualcosa di come 400 km di lunghezza di evento, una larghezza dell'ordine 30-40 km, una velocità di trasporto dell'ordine dei 70 km orari, o circa 20 metri al secondo. Queste velocità di trasporto io le ho comparate con il radiosondaggio, e vediamo che sono velocità tipiche in quel giorno, ovviamente, a quote dell'ordine di 5.000 metri o anche di più. Quindi, detto questo, andiamo a caratterizzare un attimino l'evento. Prendiamo innanzitutto come caratteristica la riflettività massima. La riflettività massima durante l'evento, vediamo che il massimo della riflettività massima più o meno è rimasto costante, mentre la riflettività massima media è diminuita, e questo è banale perché effetti ovviamente di dispersione e di accumulaterra. L'altezza della riflettività massima ci dice che la nuvola di CHAF ovviamente è scesa, sia per un effetto di gravità, ma anche perché i venti che si sono visti in quella giornata erano dei venti anche di Fen, quindi dei venti tipicamente catabatici, e quindi tutta la nuvola sostanzialmente, una volta che ha passato il confine svizzero, è scesa con una velocità abbastanza, almeno stimata da noi, in modo abbastanza grossolano, abbastanza veloce, quindi dell'ordine, stiamo parlando 70-80 km orari, poi si è portata in pianura, dove ha rallentato. Penso di essere molto lungo, quindi vado velocemente. Ok, questo non ve lo faccio vedere, semplicemente lo descrivo velocemente. L'altezza della riflettività massima, un po' mischiata, prima un radar poi l'altro, per far capire un po' di che altezze stiamo parlando di questo evento. E le altezze sono tipicamente tra i 6.000 e i 2.000, quindi la nostra analisi si è concentrata sostanzialmente in quella fascia di altezze. Passo velocemente alle variabili polarimetriche significative per quell'evento. Il range quindi è stato ristretto tra 1 e 7 km, in cui eravamo un pochettino confidenti di trovare delle signature del CHAF, e sostanzialmente quello che abbiamo visto, forse la variabile polarimetrica più importante, la correlazione HV molto bassa, quindi dell'ordine di 0,3, che è rimasta abbastanza. Qua ci sono due, nell'asse delle X abbiamo l'altezza in cappi da 1 a 7 km e questi sono diciamo, due eventi temporalmente distinti da 30 minuti. Poi qua abbiamo l'andamento della correlazione e ZDR. Diciamo che sostanzialmente quindi la variabile principale che ha discriminato l'evento è la correlazione che a una certa quota incomincia a stabilizzarsi, quindi alle quote basse più clutter terreno, mentre alle quote alte questo era l'effetto del CHAF. Questo è per il radar di Desio, questo è per il radar di Flero, un po' più sporca diciamo la descrizione, ma sostanzialmente riflette questo. Una differenza di una ZDR che si è attestata tra 4 e 10 decibel, quindi con una prevalenza orizzontale, come vi ho detto, per effetto della disposizione del CHAF in aria. Altra grandezza, ovviamente, la KDP 0. Quindi anche questa un'altra variabile che diciamo, conferma che non è un evento meteo. E questa caratteristica ovviamente è stata durante tutto l'evento. Poi abbiamo utilizzato quindi il classificatore, come accennato prima, della Vaisala, che risponde anch'esso a una logica a fasi, molto simile a quella che è stata descritta precedentemente, in cui però c'era stato anche un addestramento del CHAF. Quindi, conseguentemente, diciamo che il classificatore ha fatto il suo lavoro, la maggior parte del segnale è stato classificato non meteo, però abbiamo voluto così fare un piccolo check. Abbiamo voluto mettere alla prova il classificatore facendo un check pre-evento intorno alle 8 del mattino e alle 8 di sera e poi durante l'evento. Il clutter, diciamo, è stato il clutter che è in colore arancio, più o meno è rimasto abbastanza costante. Quello che è variato invece è la classificazione di eventi meteo che via via è aumentata durante l'evento di CHAF. Sono aumentati i casi meteo, ma non è aumentato il false alarm ratio. Cioè, sostanzialmente, se noi andiamo a fare la percentuale degli eventi degli eventi classificati meteo durante la fase di CHAF, vediamo che il FAR sostanzialmente non è peggiorato, e questo da questo punto di vista almeno è una cosa positiva. La classe meteo che è stata più riconosciuta in modo falso dal classificatore è stata una debole precipitazione stratiforme che ovviamente noi abbiamo voluto un pochettino analizzare meglio. Quindi, ok. Vado velocemente, quindi andando a vedere che cosa la QPE, le varie QPE, una polarimetrica, una standard, vedono di quella classe meteo. Vediamo che sostanzialmente in alto abbiamo la traccia della precipitazione in 3 ore cumulata da una QPE standard, mentre in basso abbiamo la traccia di quello che è una QPE polarimetrica in cui è presente anche il ZDR. ZDR dove ovviamente quando è molto differente da 1, al denominatore dà un peso maggiore e fa abbassare la precipitazione, diciamo, la la precipitazione calcolata in questo modo. E quindi sostanzialmente utilizzando una QPE con un fattore ZDR a basse soglie, in questo modo permette di diminuire sicuramente la falsa precipitazione dovuto a questo evento di Chaff. Vado velocemente sul vento, non discuto troppo, ma solo per dare qualche ordine di grandezza. Diciamo, abbiamo un task ottimizzato per il vento che va a discriminare sia una velocità dell'ordine dei 30 metri al secondo, e vediamo che nella fase finale dell'evento, in prossimità di Mantova, siamo quasi al limite del nostro range con questo tipo di processo. Il vento viene discriminato intorno ai 15-20 metri al secondo. Abbiamo fatto, quindi l'ultima cosa che vi faccio vedere è un check anche utilizzando i motion vector, sempre Lucas Canade, un po' quello che abbiamo visto ieri, e utilizzando due dataset, quello di Meteo Svizzera e il nostro, le velocità sono compatibili con le velocità dei radiosondaggio, con le velocità Doppler, e sostanzialmente la differenza è che Meteo Svizzera vede una diminuzione delle velocità nel punto in cui il blocco è maggiore all'inizio dell'evento. Diciamo, per questi motion vector non abbiamo fatto filtri di rumore né nulla, quindi abbiamo preso così com'era, anche perché diciamo, i segnali erano molto, molto bassi. Comunque, in ogni caso, anche questo ci dà conferma un pochettino degli strumenti che stiamo utilizzando. Quindi questa era l'ultima slide. Sostanzialmente questo è stato un caso abbastanza interessante, non da un punto di vista meteorologico, ma più che altro da un punto di vista radar meteorologico. Le grandezze principali polarimetriche che hanno discriminato l'evento, quindi sono la ZDR, la correlazione HV, la K di Φ 0 ovviamente, e poi anche utilizzato come test dei nostri strumenti, tenendo conto che, come abbiamo già detto, siamo piuttosto giovani e stiamo testando un pochettino gli strumenti che abbiamo a disposizione, mettendo le mani anche a strumenti un po' più complessi, sempre cercando un pochettino di capire che cosa abbiamo tra le mani. Ovviamente ora le questioni le pongo io, curiosamente. Ci siamo domandati, ma per questi tipi di esercitazioni ci sono dei trattati, ci sono delle convenzioni nazionali e o internazionali? Esiste un protocollo, un registro condiviso? Questo ovviamente lo chiedo a Renzo, che è quello che ci ha fornito diciamo, l'informazione. E poi la domanda secondaria, ma una curiosità che era mia, che volevo dire stamattina, ma se radar noi ovviamente stiamo trattando il banda X, ma considerando anche altre bande, possono essere utilizzate per monitorare incendi boschivi, grossi incendi boschivi e o diciamo grossi incendi industriali, tenendo conto che in Lombardia il rischio incendi via via un po' si sta mitigando, mentre il rischio di incendi industriali sta aumentando. La domanda ovviamente è se possiamo utilizzare questi radar per questo monitoraggio.
Grazie Antioco. Abbiamo una nuova casistica da codificare in IT Alert, mi sembra. Ci sono domande? Immagino curiosità. Ok, allora direi che possiamo Sì, grazie nuovamente, possiamo chiudere la sessione e non so, da remoto, qualcuno? Nulla? Per curiosità, quanti partecipanti ci osservano da remoto? Insomma,
abbiamo
40 stoici.
Abbiamo punte più alte.
Va bene, allora di nuovo ringrazio tutti i partecipanti, non so ora come si articola il proseguio. Io penso di abbiamo conservato il margine o il negativo.
Adesso darei la parola a Luca Baldini, che è il moderatore della tavola rotonda.
Sì, vorrei cambiare un po' il format perché sì, diciamo, a questo punto il programma prevedeva, perché era mezz'ora fa, ma anche di più, una tavola rotonda sull'aggiornamento della rete radar nazionale. Allora, diciamo, facciamo una struttura ridotta, non c'è il rappresentante di PC, che invito Vulpiani a sedersi, e invito anche perché siccome non siamo stati i primi a fare un intervento così importante di aggiornamento della rete radar, ma abbiamo anche un esempio importante, che è quello dell'aggiornamento della rete americana, che diventò una rete radar da Doppler e doppia polarizzazione all'inizio degli anni 2000, e poi un aggiornamento si è concluso più tardi. Quindi abbiamo da imparare, quindi I invite our guest star, because he played a key role in the upgrade of the NextRad network, so he can say something. Let's say, lesson learned, some suggestions for us to make effective this improvement. So can you join?
Grazie. I wish I could speak in Italian, but yeah. I understand and you understand the English. So.
But your English is perfectly understandable. So first, let's Gianfranco explain the plan, and then.
Okay, it's difficult to explain in Italian, so I guess that in English is even worse. Yes. Okay, let's have a plan. Yes, we have a plan. Well, we have maybe the possibility to use the funding that Europe provided to Italy to recover from some emergency situation during the past years. These economic resources are enough to update the weather radar network. The problem is that we have to conclude this upgrade in a couple of years, 2 years and a half, and we are still finalizing the project phase. So it's a very complex and challenging project. In Italian, okay? Just to provide.
This is the basic speak.
Okay. In Italian, I switch in Italian. Okay. Okay. To be more efficient. Okay, this is not just a characteristic of this conference, but of the Italian country, and this is one of the problems to finalize the upgrade of the Italian network. Ok, il progetto, I I hope that Professor Zernish will be able to understand my Italian. Ok, il progetto... Parlo piano. Il progetto è partito sostanzialmente un anno fa, si è conclusa la prima fase preliminare 6 mesi fa con una ricognizione a livello nazionale che ci ha consentito di appunto capire quali fossero le esigenze dei vari partner, delle varie regioni principalmente. E conclusa la fase preliminare, il progetto preliminare di approvazione è stato pubblicato, credo fosse da marzo ed aprile. Ecco. L'obiettivo è quello di concludere auspicabilmente entro questo mese, anzi diciamo entro una decina di giorni al più, la progettazione definitiva e di andare quindi successivamente, di consentire di andare a gara al Ministero dell'Ambiente, al MASI, il Ministero dell'Ambiente non ricordo mai la sigla, scusate, l'acronimo. Concludere la progettazione entro questo mese e quindi andare auspicabilmente a gara a partire da settembre. Il progetto preliminare prevede l'aggiornamento di tutti i sistemi radar in banda C e X esistenti e potenzialmente l'installazione di nuovi o la fornitura di nuovi apparati in banda X soprattutto, ma non solo, anche di 3 nuovi apparati in banda C. La priorità per quanto riguarda le nuove installazioni naturalmente per i radar in banda C che ci consentono di estendere in maniera importante la copertura soprattutto in aree che al momento sono scoperte, ma non solo, in particolar modo i nuovi radar in banda C sarebbero previsti in Puglia, in provincia di Cremona, in particolar modo a Spino d'Adda, provincia di Cremona, giusto, e a Livorno, mentre le installazioni in banda X si suddividono in installazioni di apparati fissi e apparati mobili. Quelli mobili andrebbero a sostituire quelli già presenti e verrebbero altresì acquisite da alcune partner regionali che hanno optato per questa opzione. La difficoltà sta appunto, come dicevo in premessa, nel rendere possibile tutto ciò nei tempi stretti che abbiamo a disposizione e quindi naturalmente dovremo, strada facendo, nelle prossime settimane verificare la fattibilità delle installazioni nuove, quelle in banda X in particolar modo, perché in molti casi abbiamo delle indicazioni di massima ma poche garanzie sul fatto che si possano ottenere i permessi per poter installare. Ecco, questo è il quadro di massima. Chiaramente uno dei temi che è emerso è quello naturalmente siamo tutti incuriositi dallo stato solido. Uno dei temi che è emerso è se procedere aprendo a questa tecnologia o meno. Naturalmente, a parte la curiosità, dobbiamo far fronte a quella che è anche avere un approccio anche relativamente conservativo da un certo punto di vista, perché se è vero che ci sono delle prospettive molto interessanti, dall'altra parte dobbiamo far fronte e dobbiamo tener conto di quelle che sono le esigenze operative e quindi non peggiorare naturalmente rispetto a quella che è la situazione attuale e quindi avere delle garanzie che effettivamente la nuova tecnologia possa invece portarci dei miglioramenti. Quindi ci sono in corso le ultime valutazioni su questa possibilità. Alla banda X abbiamo già aperto nel progetto preliminare, valutiamo se e come farlo anche per la banda C, considerato che è quella che i radar hanno un maggiore impatto sulle attività operative della rete.
Grazie dell'aggiornamento, della spiegazione di questo piano, perché immagino che le regioni sono state in qualche modo coinvolte, quindi alcuni elementi erano noti. Ma la domanda per il professor Zirnich is, we are not able to keep the time schedule even in a conference like this. So it is challenging because the big call, the call for procurement will be launched in September. So we will be able to finish everything in 2 years within.
You will not.
You.
No.
Yeah.
I have to interject. I have to interject. In 2001 or 2 or 3, we built signal processor for the WSI-ATD. Weather Services said, no, we are going to buy one. Sigmet will provide it and they'll be on time. I raised my hand and I said, $1 to 100. I'll give you $100 to 1. I will bet you will not do it. Everybody was quiet. And I would have won. Because it happens to be like that. It's always, you're always over-optimistic. And when it comes up to such large projects, there are delays. And I don't know, let's go with what you had to say, because I can add more, but...
Yeah, no, please.
Oh, well, okay, well, examples are... Well, examples are... Doppler is WSR-888D, 1988. It was built. Prior to that, testing started in 91 in Norman. They had a bunch of military people that were testing everything, and they found lots of problems. I don't want to talk about the problems. So ultimately, it took them about a year or more to accept. Then after the acceptance, they finished in 1997. At that time, there was, of course, we were doing the research. NSSL is part of NOAA, part of Ocean and Atmospheric Research Group. Weather Service is separate, but we are the arm of the Weather Service. We exist because of them. So we are doing all this research with upgrade to the processor, and I just told you what happened. They didn't accept our processor. I'm actually grateful that they didn't, because I would have had to do a lot of work on something that was a repetition. But we were therefore able to go into phase array, and we'll talk about that. So that big upgrade was still delayed. The Sigma processor was delayed by about a year or more, and I'll give you a detail. Passarelli, who's my friend, came and said, I can give you this, I can give you dual PRF, I have all of this. The Weather Service said, we don't care about that, we have this. Passarelli had a system, it was a software control, you turn the key on and you can enable clutter filter, no filter, everything, you get more, you have a better capability, you pay more. Weather Services said, we don't care. Eventually they accepted his clutter filter, but they said, none of your software, everything is on our software, our VCP. And I told Richard, you are going to have two systems. One is for all the world that's now, and the other one is specifically for United States Weather Service. But United States Weather Service is a big gorilla in the room, 150, 60 radars that can do that. You Italians, NSSL also, we are small animal, we don't have that weight. So you will not be able to demand something extremely specific from any of the radar vendors. You may ask for some features, but they will give you that within their software, within their control. So the way that our Weather Service operates is their software completely independent of any of the vendors, and if there is any upgrade, it has to be on their terms. Third example, upgrade to dual polarization. Barron got the funding. The procurement was what we called fixed cost. The Weather Services said 40 million, I know this very, very well because I was 40 million to upgrade all the radars to dual polarization. How did they get that? Well, they talked to us because we did put on one of the WSA-ATDs that we got, we upgraded it, so we had power splitter, extra wave, got all these pieces, and we put together what these pieces would cost, and it turns out that 40 million would have been with some kind of a profit. Well, the contractor, which is Baron, I'm not criticizing Baron, let me understand, I don't want to be too hard. They assumed, okay, they are going to buy SIGMET processor, dual polarization, turnkey, and here are your variables. Everything that Sigma processor does. Weather Services says, oh no, it is processor, but it can be Sigma processor, but it's not turnkey. Everything that we do now, only Sigma, only on top of this, you can do the changes. And I want to give you another, and that's what they had to do that. Because of that, it was too expensive, so they had to make a small adjustment or renegotiation. It turned out it cost 4 million more, which is very little, 10% more to do it that way. This is basically the way the Weather Service operates. And now I may not sound modest, but maybe I'll tell you my decision to do the simultaneous transmission, what it was based. I knew exactly that the Weather Services, if you give them something and they had to make huge changes, they will not accept. So if I went with HV change, alternate, I knew it will not go. It will never get to the Weather Services because all their algorithms, everything that they had, would have to change. So I thought, okay, if we go simultaneous, I will tell them with the simultaneous transmission, you have one channel that doesn't know about the other one, and you get everything as you have on all the other radars, except a little loss in SNR, 3 dB loss, but you can gain some. And even we wrote about the 3 dB loss in some reports. Well, they didn't pay attention to that loss, but they were happy to go that way. And that was one most important way to make that through. So in case of the Weather Services US, they have so much inertia that any kind of a huge change is not possible. Another thing that's very important, and that's important for you now, is any technology that you accept should be routine. And I'm going to repeat that in my talk. You can have technology that's maturing, that's at the university research level. You can have some that you might say is mature, but it's a level for military. For Weather Services, that's not a sufficient condition. It has to be routine, very important. Routine so that you can buy parts. You can buy parts from various places. And that's because the Weather Services are not as rich as the military. So that's what we have learned and that's what we know. Now, in your upgrades, that is a bigger decision. I would not be able to give I can give some general advice. You have to see what you got through the country. What is the most cost-effective way to approach your issues? Obviously, being that I was involved in duopole for so long, and everybody accepted duopole as a very important upgrade, significant. It should have dual polarization. All your radars should have that. Software is extremely important. That varies very much, and in your particular case, that's where maybe university and other organizations can help you, because you have a great variety of software. It adds tremendously to the labor cost later for operational purposes. For research, it doesn't matter so much because you'll be delayed. If you don't do it this year, you'll do it next year. So software comes out to be one of the most important long-term expense, and that is where you have to put a lot of effort to choose the good one that's easily maintainable and upgraded.
I think you gave a lot of comments, a lot of suggestions that I hope that will be useful for Gianfranco, but traducendo in italiano, anzi in toscano, ha detto là non ci si fa. Ha detto within 2 years.
Yeah, I can.
The question is, do we have a plan B? A backup plan if
Plan B. You should have.
We have
To go forward.
il piano B consiste nel raggruppare l'aggiornamento per lotti, per gruppi, e quindi quelli che riusciremo ad aggiornare e ad installare entro il 2026, metà del 2026, gli altri rimarranno a bocca asciutta, ecco, diciamo così. Quindi le nuove installazioni sicuramente in banda C avranno la priorità dal mio punto di vista.
Certainly some degree of coordination and knowledge, and put down, you know, what you could do and debate internally and have a list cost versus what you can do. I will give you, accidentally, I have some of the talks and pieces like that in my talk later on that will address certain of these issues. But at this moment, if you ask me certain specific questions, I can answer, because without knowing the details, I don't want to divert, and I don't want to be in between. I don't want to be the obstacle to your lunch.
Just to clarify, we were aware about the problem and the issues since the beginning, and this is why we provided a list of priorities that will be used to arrange the tender in order to obtain some results. Even if we will not be able to complete the project, at least we will make some advance in this, based on the priority that the priority criterion are basically the need in the operational, the coverage, the feasibility of the upgrade based on the infrastructure already available, and so on. So.
Yeah, sure, you want to decide on the frequency, but you already are committed to C-band, which for Europe is pretty good. So, you know, you put these, you start from the basics, and how many new radars you would have, how many of the old ones are in a disrepair that you cannot really repair. You have to refurbish the pedestal and do lots of work. I may discuss that a little bit later. I just don't want to take too much of your time at the moment. But just go ahead if you have any questions specific.
We are taking some time to the lunch break, and we want to be here at 2:30 p.m. because there is an international session, and we have to be
on time. Exactly.
But questa è una tavola rotonda, quindi una domanda la possiamo Renzo. Just one question.
This is just more of a comment. I just wanted to be a bit more optimistic because, as Dusan said, we are not so ambitious as the Weather Service did, because you made specification for the industry to develop new systems meeting requirements that you specified. In our case, we have specifications that are already met by systems on the market. So that should make the way a bit easier.
That is, I agree, that's on paper. But one thing that I want to emphasize is you should, in your contract, you should have a period of testing and acceptance. Certain amount you devote to test and acceptance, and you may test and you find out, well, something's not good, then the vendor should be required at no cost to make it work. So that is, of course, that is our experience. We had that. They had to do the testing, beta test, when they did the dual pole. They had these 4 or 5 radars on which they were running dual pole. That was, they called it beta test. If they accept that, first initial test and beta, if that is done, then we are free. So something like this you may want to build in your procurement.
Bene, a questo punto ringrazio Dusan, ringrazio Gianfranco per le informazioni che ci hanno forniti, e in qualche modo siamo riusciti a fare una tavola rotonda che è durata meno di qualche intervento, ma insomma.
Ma una tavola non rotonda, tavola è quando si dice parallelepipedo.
Sì, non è rotonda. Quindi ci rivediamo alle 2:30 con la sessione internazionale, e nella sessione internazionale siamo puntuali perché non vogliamo far vedere che noi siamo dei ritardatari. Vogliamo fare...
Sì, vogliamo non tardi. Non tardi.
Grazie a tutti.
Grazie.
Okay, so welcome and good afternoon, everybody. So we have to show that Italians are always on time. So I think it's good to start. We have an outstanding international session today. Actually, 2 of them, but the first one, we have 3 speakers. And we start with somebody that I think you all of you know, Chandra. So Chandra, the floor is yours. You have 25 minutes, and I'll be very strict with the time. So I will give you a warning, okay? At 25 minutes, we need to really stick with the time. Thank you very much. Both of you are from Colorado. I think it's 6:30 over there, so thank you very much for joining us at this early time in the day. So, Chandra, up to you.
Okay. I am trying to share my screen, and it's making me share my whole screen instead of a window. Okay, there it is. Can you see my screen?
It's coming. Yes, you can.
Perfect.
Okay. So this I've been asked to give an overview of this so-called AQPI program, Advanced Quantitative Precipitation Information. First of all, from my side, from your side, it's buonasera. From my side is buongiorno, and thanks for giving me an opportunity to talk about this. And then, most of you know, Italy is my second home, and I regret I'm not able to be there in person, but believe me, I tried to make an effort to be there in person, but I couldn't. But without that, let's keep moving. Quantitative precipitation information is something that has been pursued before the time of Christ. And if you go look at ancient cultures, from Koreans and Indians, and everybody has been trying to measure rainfall, and we are still doing that. That shows it's a fairly complex problem. And the fundamental reason is it has got variability at all scales, both space and time. This is a massive project, and supported by Department of Water Resources, State of California, Sonoma Water, Valley Water, and then this is truly a public-private academics partnership. And my major participation in this is through CIRA, which is a cooperative institute at Colorado State University. So this is something similar to what happens in the southern part of India. The extreme precipitation challenge in San Francisco Bay Area. Atmospheric rivers are a narrow band of concentrated water vapor that transport above the Pacific Ocean. Well, this is in this place. Of course, there are atmospheric rivers all over the world. Basically, 40% of California's water comes from a handful of atmospheric rivers. This is 3-4 storms. I know that where I grew up, it's pretty much the same thing happens. And while these atmospheric rivers are vital for water supplies, but they are also responsible for 80% of flood damage. And you know, a place like California, it's extremely delicate, and then with a combination of Mother Nature, complex terrain, and also regulatory issues, year after year, we never forget to see this atmospheric river when the storm season comes. The San Francisco Bay Area, which is some of the richest real estate in the world, is 7 million people. So we had done a big project like this. That project is still going on in the Dallas-Fort Worth area. And so then this became a very important region, and then we pursued deployment of small radars. The whole idea is trying to do gap-filling infrastructure at high-impact locations. This was one of the major themes of the NSF-funded Engineering Research Center, which is the CASA program, and that this whole concept of developing this with small radars was developed during that. And here's an example. These are eye candy pictures, extreme event. And then these events can't happen, but then we need to monitor them precisely. That's the main story. This incident alone created $1 billion in damage, and then 200,000 people evacuated, and so on and so forth. And so what is the challenge we are trying to solve here, and why is this a big project? This is Bay Area, which is the place where all the high-tech companies are there, Silicon Valley. It's in complex terrain, and weather radars have been known to be a valuable tool for observing precipitation. And the whole entire US has 160 weather radars, but the whole western region, which is like a big circle here, basically suffers from very basic stuff, which is coverage issues, very sparse deployment, basically due to the mountains. And then however smart a radar you have, it cannot penetrate and see through the mountains. And it is an issue. And once you have a radar, it's located somewhere way high, and a lot of the warm rain is pretty much missed. So radars, it's a combination of complex terrain, topology, and then ability to deploy radars, and then the current structure of big WSI 88D systems. And if you have seen the social footprint of a big WSI 88D radar, it's quite big. And so the challenge, many places, the NextRad is placed too high, and then the beam is way over, and then it many times overestimates rainfall. It's always looking through ice melting region. And then we have multiple radars, and then a lot of the times, if you go back and look at how these radars were deployed, a lot of you, when you fly and when you are about to land and there is a ting sound, and then so that means you're about to land, and that happens when the airplane crosses 10,000 feet, and that's when they ask you to wear a seatbelt. That's the, radars have a connection with aviation, and then the 10,000 foot map was used in the US to look at coverage. So last time we checked how many people lived at 10,000 foot altitude, other than a few places like, we are supposed to be at high altitude, even we don't live at 10,000 feet. So AQPI is a synergistic project that solves a lot of the practical problems and also advances technology of high frequency radars to observe precipitation. But the bottom line is getting the products in a meaningful way to the end user. And in between, we publish some papers and show some cool things. That's good. And the benefit is flood mitigation and so on. So it uses a combination of modeling and observational framework. Where is the water? Is it in the atmosphere? Is it in streams, or in the ground, or in the bay? When is the water coming? Combine observations and models to create a short-range forecast. How much water will be there? And then when will it end? And is my infrastructure at risk? So essentially, these are the questions that are being asked. So it's a huge project team. So I belong part of the NOAA system that we sit with inside the Sierra, where we do all the deployments of radars. That is one of the things that we are responsible for. There's a whole bunch of county, and then they're very active and they're involved in this. And then USGS is responsible for all the ocean-related stuff. And then there's also a whole economic study, and I don't want to get into this. And then Scripps Institute, which is also a strong partner with us. So observations, forecast, stream flow, coastal flood. This is a combination of things. It's a pretty simple process in terms of how to describe it. And then it has all the Bay Area users. So what are these instruments? These instruments we should be able to deploy. This is the workhorse, which is X-band radar. This should be easy to deploy on existing infrastructure. We don't need to go by land, and etc., etc. There are so many requirements. And then these are the workhorses. These are small but mighty X-band radars, and they just sit quietly and blend in the surrounding. And then we have some in situ measurements, basically to show that this is a vertically profiling radar from NOAA, and then a whole bunch of disdrometers, everything to prove that it's working, because we are basically dealing with flood managers and water managers, and they, unless you ever compare it with something on the ground, they don't believe anything. Okay, so this is the area where we are deploying, and this is the San Francisco Bay. And then you can see the complex terrain here. And now I have, of course, have done this in meters. And we are deploying 5 X-band radars and the C-band radar strategically located to provide high resolution coverage over highly populated areas. And we have already deployed 3 radars. And then, of course, anytime you're deploying radar, you're going through frequency clearance, regulatory process, getting land, and all these things we are going on. So these radars have been already deployed at Santa Clara, Santa Rosa, Santa Cruz. And then the Rocky Ridge radar is already deployed. We are dealing with IT and other protocols. And then there will be an X-band radar at Montero Peak, that is the city of San Francisco radar. And then C-band at Bodega Bay. Well, the C-band is now, it's been moved. In addition to this, we have this big circles is the Weather Service radars. Okay, I'm going to skip this. This talk is not about radar and radar technology, but nevertheless, this whole thing was developed during CASA, and it's been successfully deployed on a 7 radar network over Dallas-Fort Worth, so you don't need it. So here's an eye candy picture of side-by-side between what is seen by today's NextRad and what is seen by CASA radars. And I wanted to show you the raw picture from the radar without any fancy smoothing, beam filling, this, that, to see the reality on the ground. Because a lot of times when you go to conferences, you see a lot of dressed up images we put a lot of clean smoothing and all that stuff. And you see these are played exactly at the same time. This is the time update. And then on the right side, the NextRad radar is looking way high. It misses all the low-level features, whereas you see this fine line that's moving through San Francisco Bay Area. And so this is, a picture is worth 1,000 words. And that's why we have the so-called AQPI radars. So one of the basic problems in the Bay Area is that 95% of the rain comes in 2 parts. One is whether it's warm rain and then lifted up due to complex terrain, or it's a simple bright band rain. And, you know, I've been developing X-band radars and then algorithms and QPE for, you know, places for the plains like Dallas-Fort Worth, and I've showed it's very, very accurate. And actually that data was used to show that, to prove, to satisfy the mission requirements for the GPM, because you needed to have some quantitative precipitation over an area that's more accurate than anything else. So in Dallas-Fort Worth right now, if the radar and gauges don't agree, they actually send people to check on the status of the gauges to see if the gauge has been knocked over, or if there's a tree that has blown over, or whatever. What you see on the top is CFAD of reflectivities, and then this one is reflectivity, and this one is vertical velocity. This is, you know, precipitation physics 101. People have seen this, and fundamentally the physics is different between the two, and then the algorithms seem to be different, and if you don't fix if you just put one blind algorithm, it doesn't seem to do well. So if you can take care of this, you've solved 95% of the problem. So I'm not here to solve the last 1% that is left, because this is end users. So if you do something robust but simple, we don't want a very complicated algorithm that works extremely well for one case but falls flat on your face 90% of the time. We need something robust that works day in and day out, because there is nobody sitting and taking care of this radars, babysitting. These are not field programs. These work day and night. So all that you have to do is recognize these features, and then once you recognize the features, tell what kind of algorithms to do. So here's some disdrometer measurements. So this is Santa Rosa, and this place is Middletown in San Francisco. And this is how you see complex terrain changes quickly. And then you look and then see features of the distribution. This is well known. And then you have warm rain as opposed to rain coming from melting layer. So I don't want to go through this because I can work with my cloud physicist to talk about this slide for 15 minutes, but Alessandro won't let me. And and then how do you recognize this? We actually recognize this with rain that comes from, we just do a simple reflectivity, differential reflectivity scattergram. But these type of rainfall, they fall under different regimes. And these are things that, like, one look at it, somebody like me could easily figure this out. Now let's keep going. So essentially you create some sort of algorithm to delineate between the two things, and then recognize this, then come up with some basic algorithms. So if you don't have bright band, and then if you have warm rain and you have large amount of small particles and few large drops, whereas when you have bright band. And long time ago, I used to work with, you know, many cloud physicists here like Bill Cotton. One of the reasons we have these big particles is because the ice core gives the stability to sustain these big particles as they melt. Whereas warm rain and collision coalescence is a different story. But the bottom line is it all has to convert to equations, and then 23 kdp as opposed to 18 kdp.8. And then these you can have, and then you also have rainfall and then reflectivity, and I have different curves to show all this. This is 101 radar meteorology. Everybody in the audience is too smart. I don't want to go through these simple things. Okay, so if you do this if you don't do this type of classification, you take one of these sites, there is overestimation and underestimation of rainfall when compared with the gauge network. Whereas you do this adjustment according to the rain type, then it sits right there. And then here is a time accumulation. This is like, I can show this for many, many storms. The solid line is rainfall from ground gauges and instruments. And then this blue line, this is directly produced in real time. It's not like we get data and then go reanalyze, adjust some things 15 minutes or next year when the curves don't look like. Everything we do in this project is real time. There is no post-analysis. People are not interested. The water managers say, no, I'm not interested in seeing what happened in last year's result. And here is the comparison right on the money. Whereas if you just did just put everything together in simple single algorithm, this is what you get. And this is the MRMS algorithm today that NOAA puts out. And and the first one is called MRMS radar only. That's the red curve. But then the MRMS has two products. One product is it just produces live, and then the second product. And don't get me, I'm not here to show how MRMS is doing that or something. Everybody knows in the Bay Area, you don't have much coverage from NextRad, so MRMS is expected to do that. So it's not about MRMS, but that's the NOAA product that we need to improve over. So I have to show this. And of course, NOAA is a partner in this. So they are trying to improve. So it's not like I'm trying to show MRMS is not good or something. So that's not the main message here. The main message is, even if we did the so-called single KDP without adjustment of the rain microphysics, you cannot do well. Okay, now there are a lot of times you just can't observe KDP because you have complex terrain, and it's very shallow precipitation. When it's and after some time, the beam is definitely above melting layer. So you have to recognize it is above melting layer, and then you have to basically take care of, be ready to observe and compute precipitation with reflectivity alone. You can't use KDP when it goes above the melting layer. And of course, you have polarimetry, so you can recognize melting layer, just it'll be in your face. And then there is one more thing that my Finnish friends have taught me. They used to make a joke. Vertical profile of reflectivity is yet to be invented in the US. Of course, this is a question and makes a joke to me. Finland, they take this vertical profile of reflectivity very seriously, because they say, especially when it's snowfall, they used to make jokes. What you measure in Finland, actually you are measuring Russian snowfall, because by the time it hits the ground, it's already in Russia. So there is a lot of vertical profile correction. So many times when you observe reflectivity, it is in the bright band, and then you have to make adjustment for this. And I know in UK, they take this bright band adjustment very seriously, but here you can see this is a typical vertical profile. And I'm actually starting to look at this very carefully over Colorado mountains also, in the Colorado River Basin, where there is another experiment going on, and I'll skip this. So finally, when you have complex terrain, this is a typical setup that you see with the hydrometeor classification. You have rain, you have wet snow, and whereas if you did a simple KDP-based rainfall, this is what you get. There's all sorts of things. In this region, it's bright band contamination. This is MRMS, and obviously the NextRad product, the NOAA product, shows bright band contamination. This is all this problems mitigated, everything put together. Every cross here is a ground validation location where people look at all these things. Let me keep going. Here is some block diagram of how all this happens. And there's a lot of brain power that has gone into algorithms, and there's a lot of effort that has gone into the computers that do all this. This is what I call as the real-time data flow architecture. And I'm sure you recognize this person here, Renzo Bicchini. He has contributed quite a bit to a lot of the products that has gone in here. And most of the hydrometeor classification has come from Bicchini's work here. So thank you. I want to give a shout out to Italian colleague. Hi, Renzo. Anyway, let's keep going. Here's a side-by-side product of MRMS versus AQPI final product. So let's do this. Let's do some more validation at the validation gauges. So for different events. And then this is one of the gauge locations. This is validation over the Sonoma County radar. This is over Santa Clara. And Santa Clara is Santa Clara, San Jose. And then between these two radars and one more radar in this real estate, you have Google, Apple, Facebook, and then to everybody combined. So it's very high value real estate, and a lot of people are watching, and very smart people there, and you get a lot of feedback. And essentially what you see is the solid line is the rain gauge, and then the blue line is AQPI QPE product. And then in this case, this is MRMS, multi-sensor pass 1, that is MRMS goes back and corrects, and then this is the radar only product. And then this is at a different rain gauge. And this is, I wanted to show you, this is 0 degree isotherm, and then these are the various products you see, and you need to estimate rainfall here, and it's verified with this. So you have this comparison issue. So, and you can see the complex terrain map, and that is faced here. And I'm sure many of you who have visited, you recognize this is San Jose, San Francisco, that's here. And then this is the north of the bay, which is the Sonoma County, which is essentially the wine country there. Okay, so you put all these into numbers, and then this is all you get. And then the problem is when you see how much disparity it is, but when you take all this and put it into RMS errors, and this is what people see in conferences, and the correlation is quite good between the MRMS, you go after the fact and correct all this, and then the QPE product, root mean square error, ours is 20 millimeter accumulation, whereas MRMS is 24, and then radar only is 39. And then between here to here is a factor of 2 improvement, but here it looks like only 5 millimeters, but when you actually go back and look at the profile of how it keeps up, it's quite distinct. That's the reason we've been throwing everything into this RMS error metric and then fooling ourselves into complacency. And I don't want to go into a big lecture about the flooding problem. Flooding problem is like a bathtub problem. Water comes into a bathtub, and then water goes out to the drain, and then the whole basin keeps on filling. And then when it comes to the top and the bathtub keeps filling up faster than how fast it can drain, then the whole bathtub flows over, and then you have a flooding situation. And there, even slight amount of error in rainfall is very important. Okay, I spent quite a bit of time on this because it's a radar meteorology conference. There's a whole another stuff that we do is DARTs. It's completely done in frequency domain and using fast Fourier transforms to keep up with high computer updates. And then even today, this gives a run for the money for all the machine learning based nowcasting that comes. In fact, people are using DARTs to start training machine learning algorithms. And this is running operationally, and then there's like a whole interface that every end user, county managers, water managers see. And if I have to talk about that, there's a whole system level talk. And I have people who are evaluating the end-to-end system, because the system engineering, this was all developed with system engineering driving the whole thing. And how much time I have?
3 minutes.
Okay.
And then questions.
Okay, let me skip this. I don't need to show how well the nowcasting is performing. So the modeling, and so what are the different domains of these models that go into the end users along with the radar product is the HER model, which is automatically coming from NOAA. And then that's the bigger domain of the HER model that goes into the forecast domain. And then you have national water models, and then then you have the QPE domain. And then you have Cosmos, which is the USGS coastal model. All these models are running in sync with this thing. And then I'm going to skip this. You can read up on high resolution rapid refresh, which is. So this is the distributed hydrologic modeling that's running in there into the system. And so all the QPE material goes into that. And again, the whole project is still under construction. But I'm just trying to tell you where all our QPE products are going in. And these are going directly to the county water managers who do this. And then there is this Cosmos, which is USGS is a partner in this, which is a coastal storm modeling that goes into this. which is again a physics-based modeling, and then based on the river runoff and then high tide, and then they give flood model, which is a combination of our QPE and then ocean model based on this and so on. So it predicts basically coastal hazards for the full range of sea level rise, 0 to 2 meters, 5 meters, and storm possibilities. They're very, I don't know what level of validation they do, but they have a pretty sophisticated model, but everything runs together in one system. That's the key thing. And it's all being managed here. It was running in NOAA, and after the initial period, it was transferred to CIRA, and then we are running these systems at CIRA right now. So we had to do economic benefits, and then there's a whole article on this, and then this is all done with the end users. And you saw before there is by category, where do they get the benefits and who's benefiting? Apparently, flood mitigation is 60%. It seems driving. I would have thought California with water shortage, that would drive that more. There is like a water economics. They sell water from different counties. A lot of the people who sit on our board and manage us are from the water managing districts. The water supply part, they benefit 14%. Recreation apparently is as important, and it's 10%. Transportation is 14%, and ecosystem service today. This is in terms of who's paying the bills, or who is thinking, who is benefiting. And then, so in terms of, so people ask, okay, you put all this infrastructure and you pay all this high-powered PhDs to do this project. Yeah, I have one damage and I fix it. Are you costing me more than what it costs to fix these things? So somebody went and studied this, and it was not us. And the best estimate for benefit is 5 to 1. Optimistic estimate is 13 to 1. And pessimistic estimate is 2 to 1. If these are people who don't believe we can improve anything. And even there, they found 2 to 1. So this is a big eye opener for me. What do I do historically? You do something cool and then write your papers and just move on with life. But it's really useful to see that somebody thinks what we do is useful other than our own community. Like, it's like a circular thing. This is somebody who's paying for things, and these people don't have PhDs, and they're managers of people. Anyway, before Alexandra kicks me out, I want to graciously come out myself. So it's a 5 radar system. 3 of them are there already. 2 additional X-band radars, and the C-band radar is on the way. And I just focused on one small part of it, which I thought, since it's a radar meteorology conference, you may be interested in this, but I also wanted to put the big picture where we sit in the big scheme of things. And we have a display. End users keep looking at this all the time, and we do this end user training and this and that and all that stuff. So, thank you. I will end here.
Yeah, thank you very much.
Thank you very much.
So I think we have time for some questions. I think Italy is a nation of complex terrain, so I think people here is interested very much in your talk and your techniques. Anybody?
Can you see me, or am I still sharing the screen?
Yes. By the way, Renzo is in the room, of course.
Hi. So one of my dreams is to put one of these radars in Amalfi Coast. You cannot get more complex in complex terrain, right?
Nobody? So maybe I make a question. So
I'm a post-line speaker, so that's why no.
Now, so I have seen that you use this rainfall KDP relationship at short ranges, but does it apply to all kind of rain regimes? I mean, I guess if it's light rain, it's breakdown somehow, or?
Yeah, so this is X-band. So we use this because it has to be over a length. And Renzo can explain this to you. We have a fancy algorithm. So if the rain is light, I've even actually established RKDP at sub-millimeters at going into KU band. And so there's enough particles that there is a paper where actually estimating KDP at KU band using E3R radar for NASA. And so we produce it over a length, and then over the length there should be sufficient KDP. And of course, if the KDP is not measurable, we have a data metric, then we resort to RZ. 9 out of 10 times, if it doesn't cross 20 to 25 dBz, there is really not much rain happening.
Yes.
But I mean, rain hitting the ground. But if you're around, I showed you the ZZDR scattergram. I can go to the figures and show it to you. But we do have a RZ equation to fill it in if KDP doesn't work in. But I have bigger need for RZ when the KDP goes into the ice region. That's a bigger problem because there is not KDP to measure.
I see, yes. Okay, so maybe another round of applause for Chandra. Next time, we hope to see you here. Guess next RadMet will be, we already know where it will be. Anyhow, so in Italy. So, okay, thank you very much, Chandra.
Thank you. Bye.
And okay, next. Okay, I don't know what happened here. Okay, next speaker is Professor Susan van den Nieuwe. She is from Colorado State, and she will discuss about this NASA INCUS mission that will be launched in a few years. So, the screen is yours, Sue.
All right, Alessandro, thank you. Can you hear me?
Yes, very well. Just put in full screen the presentation and we are ready to go.
All right, let me see here. Okay, hold on a moment. I have lost the bottom part of my screen here, so let me just see here. Can you see that?
Yes, perfect.
And it's in full screen, yeah?
Yes.
Perfect, okay. All right, so thanks very much, Alessandro. Thanks for the invitation to talk here today about the new NASA INCUS mission, and good afternoon to everybody. Chandra and I here on an unusually rainy, cold Colorado morning, actually. We had one of the coldest temperatures here in Colorado yesterday, but it's good to get the rain. So anyway, let me start talking a little bit more about the NASA INCUS mission. You can see there's a lot of people involved in this mission, and I'm very grateful for all of their contributions. All right, so I'm going to start today just giving you a sort of broad overview of the science of INCUS, and then I'll talk to you a bit about the setup and instrumentation that we're using. So INCUS, or the Investigation of Convective Updraft mission, the primary goal of this is to understand why, when, and where tropical convective storms form, and why only some of these storms produce extreme weather. And before I get going, I'm sure most of this audience is more than familiar with convective mass flux, but in case you haven't come across it, this whole talk is about convective mass flux. So if you don't know what that is, it'll be a meaningless exercise. So in essence, convective mass flux, if you take a slice through a convective storm and look at the transports that are going on within deep convection, of course, the convective mass flux is simply the vertical transport of air and water through convective storms. And so INCUS actually will provide the first ever tropics-wide observations of convective mass flux within tropical convective storms. All right, so why care about convective mass flux? And of course, it's important on a wide range of scales, all the way from the large-scale circulation through to storm scales and even smaller. And we've known for more than 70 years that storms that develop in and around the equatorial regions, these facilitate the rising of air, right, lofting up to the upper troposphere. And of course, air that's lofted to these levels has to come down somewhere. And so it's, this air subsides in the subtropics. And it's this rising of air within the equatorial regions that establishes these moist regions. and the sinking or subsiding air that establishes dry regions. So it establishes these local moist and dry climates. And as I say, we've understood this for about 70 years and the role of deep convection in driving this large-scale circulation. However, what we don't know is how changes to the convective mass flux, be this due to climate change or other changes, how this might impact this circulation with feedbacks then to regional climates. So this is why we care about convective mass flux, or this transport of air and water through storms on the large scale. And then, of course, this audience is more than familiar with why we should care about convective mass flux on the small scale, be it from the production of fresh water by storms all the way through to the generation of extreme weather. And I'll come back to this in a little bit. So when proposing these large NASA missions, we have a number of science objectives. These are very high-level objectives. There's a lot more sub-objectives, but I'll just talk to the four main primary science objectives of NCIS. And the first one is to determine the predominant environmental properties that control convective mass flux within tropical convective storms. So we're trying to understand the role of the environment on controlling convective mass flux. A lot of great work has been done in this area for sure, and we have a good understanding in some areas as to how environmental properties like the moisture or vertical wind shear, how these drive convective mass flux, but there's certainly gaps in our understanding in this regard. And this example demonstrates this. If we look at equatorial Africa and we look at equatorial South America, these are regions that have arguably very similar environments, and yet the storm properties in terms of the intensities of these storms, how high they develop, the kinds of precipitation they produce are actually really quite different. So we've got a long way to go in terms of understanding the controls of the local environment on storm properties, and that's in current climates. Of course, if we're going to understand what this means in future climates, we need to understand how environments will change and hence the feedbacks to convective mass flux in future environments. So in essence, we still do not have a unified theory of environmental control on convective mass flux, and this is the first science objective of NCIS, is to contribute to this. The second objective talks to convective mass flux and high clouds, and in essence, what we want to understand now is how convective mass flux sort of drives the properties of convective anvils. Of course, we know this is really important to cloud radiator forcing, and hence the regulation of atmospheric temperatures. And that element of convective anvils, again, the interaction of anvils with radiation is relatively well understood. But what is not understood is whether or not anvils actually get wider or narrower or thinner or thicker as this vertical transport or as this convective mass flux changes. Also, we don't understand really how anvils will change in future climates. This interesting paper by Sandrine Bonny and co-authors suggested in future climates that in essence cloud tops will get higher and anvils will shrink. But this is conducted with GCMs, and we know we've still got quite a lot of work to do in terms of appropriately representing the links between the dynamics and the microphysics in GCMs. And so we're hoping that NCIS will help us to assess how this transport of air and water talks to anvil characteristics, both in current and future climates. The third objective of NCIS then is also to look at the impacts of convective mass flux, but now on current and future weather. And in essence, what we want to do here is assess the relationship between convective mass flux and the type and intensity of the weather produced. And so we know certainly to first order, there's strong links between the transports in storms or the dynamics of storms or the updrafts of storms and the kinds of precipitation that these storms produce. Chandra alluded to some of this in his talk. But what we don't know, right, is whether the strongest storms produce the most intense rainfall, the highest lightning flash rates, and so on. And if you look at this figure here, which in essence shows the 99th percentile of rain rate as a function of maximum updraft speeds, again, there's a first order relationship, but this relationship is far from linear. So there's a lot that we need to understand in this regard. And Chandra alluded to this, the broader community. The broader community is also very interested in extreme weather. We're all aware, whether you're reading the news or in your own areas. I know Italy's had very serious floods recently. People are aware of extreme weather. This is a figure from the World Economic Forum publication in 2020. They spend a lot of time assessing those events on Earth that have the greatest impact and the highest likelihood of happening. And if you look at this top right quadrant, which are those events with the highest impact and the highest likelihood, we see extreme weather sits out here, which is that event which has a very, it has a very high impact on mankind, perhaps the second or third highest impact of all these things they've considered with the highest likelihood of happening. And so there's really a lot of questions around this in terms of why is weather becoming more extreme, and then of course how do changes to convective mass flux impact extreme weather. And then our final objective is to take the relationships that we've learned or obtained from the first three objectives and to assess them as to how well they're represented in models across the scales. And so if we look at models across the scales, we all know there's a wide range of forecasting models that we use to our benefit. We start on this side, of course, we have numerical weather prediction models, which have grid spacings on the order of 1 to 3 kilometers. They have regional domains. And of course, they are able then to explicitly represent convection or explicitly capture those convective motions. But a lot of recent publications, including this one published in 2021, this was a model into comparison of a wide range of state-of-the-art numerical weather prediction models across, this is an international collaboration, and you see that predictions of convective mass flux or the vertical velocities differ by a factor of 3, especially above the freezing level, across these state-of-the-art numerical weather prediction models. So clearly we've still got a way to go in those models that explicitly represent convective mass flux. And then of course on the other side of the temporal and spatial scale, we have our global climate models, grid spacing on the orders of 25 to 100 kilometers with global domains. And by virtue of their grid spacings, of course, they have to parameterize convective mass flux or represent the effects of convective mass flux. Now, because we don't have global observational database of convective mass flux, in developing these parameterizations, global climate modelers are forced to go back, of course, to numerical weather prediction models for the representation of convective mass flux. And of course, we know that the NWP models have their own issues. There's very exciting developments, of course. Most of you are aware, I'm sure, of this move now to K-scale models, where in essence we have global weather models, grid spacing of 1 kilometer with global domains. This is a fantastic development. It's going to be awesome to have simulations around the globe at these kind of resolutions. But even taking it to these resolutions, we still face the issues in and around convective mass flux that our numerical weather prediction models face. So obtaining or building a global observational database, and by that I mean all around the tropics, of convective mass flux within tropical convective storms, really will help us evaluate our models across the scales, as well as build potentially better parameterizations in our large-scale models. All right, so that's really the sort of science around INCUS. Let's look now a little bit more at the INCUS mission. And in essence, so what are we going to do, and what does the INCUS mission actually look like? So in essence, we're flying 3 small sats. So they're separated in really short intervals in time. There's 30 seconds between the first and the second, and 90 seconds between the second and the third. And on each of these small sats, we will have a Ka band radar. This is a multi-beam. It's a 7-beam radar, so it scans cross-track. This is a lot of RainCube heritage. Of course, the RainCube was a native pointing radar. These do have a multi-beam capacity or capability. So each one of these platforms or small sats contains or carries one of these Ka band radars. These are built by JPL. And then on the middle small sat, even though it's indicated here for schematic purposes, on the middle small sat, we'll be carrying a Tempest D-like radiometer. Of course, this is a lot of work that Steve Rising and Chandra were involved in here. JPL will be developing or building this radiometer. And as I say, it sits on the middle small sat. We have commercial partners. Actually, these are 2 Colorado companies, which is really nice for us here at CSU. In essence, Blue Canyon Technologies are building the bus. And then, of course, as you all well know, if we're going to be operating radars, we're going to need some kind of antenna, and Tendek is going to be building these deployable antenna. In essence, by separating these 3 small sats in these short intervals in time, we can rapidly sample the same storm systems, right? Thereby allowing us to go after the evolution of convective mass flux And we are now in the process of applying this really novel time differencing approach, in essence, to allow us to retrieve convective mass flux. And I'll talk a little bit more about that in the next few slides. Each of these spacecraft, people often like to know the size of these. They weigh about 100 kilograms, about the size of a microwave oven. Because this is a tropical mission, we will be at an inclination of 35 to 39 degrees and launch. Right now, we're on target for August of 2026. So this is just a movie, in essence, showing what the mission will look like. I hope it's not too jumpy on your side by virtue of the bandwidth. This shows the first spacecraft. You can see the antenna deployed there. This is the lead spacecraft carrying that Ka-band radar. We now see the second spacecraft entering the image. This is carrying the Ka-band radar as well as that Tempest D-like radiometer. And then the third spacecraft following 90 seconds after the second one comes into the picture and is carrying one of those Ka-band radars. As I said, tropical inclination, launch date in August of 26. And these, this image shows, in essence, the spacecraft flying really close together, allowing us to sample the same spot on the Earth in time, allowing us to ensure we're sampling the same updraft. And then this next image, in essence, shows us what we obtain from the radiometer, brightness temperatures at storm tops, right? This gives us a lot of information about convection. And of course, flying these, as the last image will show, flying these instruments together, these radars and the radiometer together, really provides us with this extremely novel three-dimensional view of storms. And we're hoping that that's really going to advance both the science and the prediction of storms. Okay, we don't want to do that. Let me see. Okay, so I mentioned this unique time differencing approach. We know that convection evolves very quickly. What this shows is a convective storm growing in height, and each of these images are separated by 2 minutes. And in essence, if you have an updraft speed of 15 meters a second, this corresponds to a growth rate of 1 kilometer per minute. So if we're rapidly able to sample a cloud system in time, clearly this provides us information on storm motion, on storm transport, and hence on convective mass flux. Put in a bit of a more graphical manner, these are some nice images that Pavlos Kolias gave to me. These are images through a deep convective storm produced through the use of OSSIs. This demonstrates the INCUS approach. Here's the first satellite at 0 time, 30 seconds later, and 120 seconds later. And if you just focus, for example, on one of these isosurfaces, say the 40 dBz isosurface perhaps, you can see the motions of these isosurfaces in time. And by virtue of that, we can back out information about transport and motion. Perhaps put a little bit more quantitatively, this is from a paper that actually recently, it just came out a couple of weeks ago. This is from a suite of OSSI experiments that we've been doing. What's shown in the top panel is the reflectivity through a really nice deep convective mesoscale convective system. In the middle panel is the reflectivity 90 seconds later. So this is the change in reflectivity through the system. And then in the bottom, in the green, we have column maximum values of vertical velocity. And in red, we have column maximum changes in reflectivity. And in essence, and this is just one example, we've looked at hundreds of these in essence, but in what this is showing then is that in the regions where we have the greatest changes in reflectivity, these occur or are manifested where the updrafts are strongest. And we're finding that this is with a correlation coefficient that's greater than about 0.7. So we're now very busy characterizing this relationship then between the changes in reflectivity and vertical velocity. And a lot of work is on the go through the use of these OSSIs, and I'll talk a little bit more about that in a moment. So people often ask why the differences in time, right? Why 30 seconds and 90 seconds and 120 seconds, and how does this really help you? Why not fly them the same distance apart? And in essence, again, through our OSSIs, what we've determined is that this time interval, the 2-minute time interval, it really comes down to balances between our abilities to detect the updrafts as well as this low false alarm probability. So 120 seconds allows us to detect 95% of the updrafts with a really low false alarm probability. It's less than 5%. In our short time interval, this 30-second time interval, this allows us to make more correct estimates of our strongest updrafts. And then, of course, this moderate time interval, which is really just the difference between these two, is really just a robust compromise between our capabilities of detecting updrafts and our false alarm probabilities. Detection goes down a little, false alarm goes up a little in this compromise. So this delta T approach actually has been really exciting. It allows us to study these different parts of the convective mass flux intensity spectrum by virtue of having these different time intervals. It also allows us to actually quantify the duration of vertical transport, which is very important for the assessment of models. And then it allows us to look at the evolution of deep convective storms, which, as I mentioned a few slides ago, and which you all know evolve very quickly. Oops. People often ask, so why not replace this whole thing with a platform with a single Doppler measurement? And it's a great question. There are certainly differences. If it was a single Doppler measurement, we could certainly characterize the instantaneous vertical velocities, but it wouldn't provide us information for how long such a speed is sustained, nor information on the evolution part of this problem. So, you know, my view is it's great. It would be great to have both. We really hope that we can actually get platforms flying Doppler, and of course NASA's AOS efforts will provide this or put this in space. And of course, JAXA is now sending up Doppler velocities. So in order for us to build out the best possible data sets, it's really great to have both in space. All right, so in terms of the INCA's science and algorithm approach, as I said, we're now doing a lot of work in relating those changes in reflectivity to the convective mass flux or to storm vertical velocities. And part of this is been through the development of these extensive OSSEs. So we've generated an extensive database of really high resolution simulations of convective storm systems. We're simulating a wide range of storm types in all sorts of different environments within the tropics. This figure here on the right shows you some of the regions we've simulated already. We're making use of both the RAMS and WRF models, so we have different sophistication in terms of the microphysics. And we're conducting these simulations on grid spacings of 100 meters, which, if you're not a modeler, this is a remarkably high resolution. It allows us to resolve that transport within storm systems or resolve those convective motions. This has never been done before, and it's been a really interesting scenario in terms of model development. And where I say never been done before, done on this kind of scale on these really large grids. And it's only facilitated by the fact that we've had extensive core hours on the NASA supercomputer systems. We output model every 30 seconds. We've done 15 to 20 case studies already in phase B, and as we move into the next phase of the mission, we'll have another 30 or 40 case studies coming. After we've produced these simulations, we then go about tracking storms. So we need to track storms in order to understand what the updrafts are doing. We make use of a storm tracking tool. It's actually this towback tool. It allows us to explicitly track on storms as demonstrated here. So this is just showing one of the simulations. This is out over the Philippines. And the different ISO lines here just show the different updraft strengths that are being tracked in each of these storm systems. And for each of those tracked storms, in essence, we produce this information. So this is probably of the greatest interest to this audience: cross sections of vertical velocity, the total condensate, and then the radar reflectivity at the INCA's footprint. As I say, for each of these tracked storms, we have this information, and the community more broadly is actually very interested in these tracked snapshots, and we're certainly open to collaboration. If this is something of interest to you, please just ping me, and we can certainly talk more about that. Let's see if we can get to the next one here. Okay, this just puts those in a little higher resolution. Again, the vertical velocity, let's just play both of these. Vertical velocity, total condensate, and then what the INCA's footprint would see, the reflectivity on the INCA's footprint. These are not at the same vertical heights, it's offset. This goes up to 14 and this is 20. But let's just play it down here in the slow mode again. And in essence, you can see what INCA's would see if flying over this scene. So we've been doing a lot of these kinds of experiments. Okay. After running the simulations, tracking the storms within the simulations, we put all of this information through some pretty sophisticated forward models. These have been developed at JPL, data converted, of course, to the Incus Ka band reflectivity. And as a result of this process now, we have millions of tracked updrafts. And at the end of the process, we will. Right now, we honor about several 100,000, and by the time we get through the end of phase C, this number will be on the order of millions. So it's really exciting. It allows us to do all sorts of things that have a great sort of variety of statistical robustness. And then, of course, ultimately, what we do is we hand over these tracked scenarios. What we're doing is we're producing 2-minute tracked situations to match the Incus footstep. We hand these over to the algorithm team at Ziad Haddad and all of his team, from where we now, in essence, making use of a lot of machine learning and so on in the development of our retrieval algorithms. A couple more things before I wrap up here. A lot of you clearly in the radar community know that if we provide a slice through convector storms, we actually don't know where we've taken that slice through. Have we hit the updraft? Have we hit the anvil? And so on. So having the radiometer on board, right, the Tempest D-like radiometer on board, provides us with a lot of information as to where that sample is being taken. You know, are we hitting, these are the cores of the ice water path or elsewhere? Are we out over in the anvil or elsewhere? Because this is really important for us to be able to characterize the convective mass flux on a storm-to-storm basis. Of course, does ice water path, do the highest ice water path cores necessarily correlate with the updrafts? From physical principles, they probably should by virtue of a transport argument. And so we've been using this extensive database of these really high resolution model simulations to look into this correlation, and we actually find a strong correlation, particularly between the integrated water path and the maximum vertical velocities obtained. So we're making use of this information to help us provide context ultimately as to where the Incus radar observations will be made. And then lastly, we've been doing quite a lot of work making use of ground-based radar to assess this Incus delta T approach. This is work that Brenda Dolan's been doing with Pavlos Kolias and others. In essence, what we've been using are data from the recent Tracer and Escape field campaigns. These were DOE and NSF campaigns conducted in and around Houston. They made use, in essence, of Pavlos and group and collaborators' new approach of this multi-sensor agile adaptive sampling approach, or this MAS approach. And in essence, what that allowed them to do in the field is automatically detect and follow deep convective cores. And so they were able to provide vertical cross-section, those are the RHIs, at high temporal resolution, 20, 40, 60, 90, 120 seconds, all matching the Incus delta Ts. And we picked a number of cases out of those field campaigns then in order to optimize the dual Doppler configurations, so that this allowed us then to look at the changes or the changes in reflectivity with time and assess them against what the dual Dopplers saw. So this is just one example. Again, we've done a number of these examples. This is a cross-section through one of the deep convector storms seen in Escape. This is the reflectivity 30 seconds later and 60 seconds later. This panel here on the middle right is the change in reflectivity after 30 seconds and after 60 seconds. And then in essence, this is the derived vertical velocity as a result of processing this using Samurai. And to first order, we're very relieved to see that the changes in vertical velocity actually correspond really closely or really well with the Doppler-derived vertical velocities. Of course, you should be saying, well, hold on a moment, Sue, this is, that's ground-based radar, that's at a resolution, that's a really high resolution. Incus footprint is on the order of a little more than 3 kilometers. Are we going to see similar things from space? So this panel, again, comes back to the ground-based radar at the ground radar resolution. Same cross-sections in the top panel, change in reflectivity at 20, 90, and 120 seconds. Sorry, these are cross-sections at 20, 90, and 120 seconds, and these are then the changes in reflectivity. And if you scale this to the Incus footprint, we find that we still pick out a lot of those elements of interest to us. Incus is focused on storms above the melting level. A lot of these features are picked up at the Incus footprint, which is fantastic. So using this ground-based approach, we're very excited to see, to first order, that we can demonstrate this delta T approach, and there's several papers in the process of being developed on this, and we're now taking the deep dive, of course, into all the different terms making up the vertical momentum equation. The INCUS science team, it's a very large science team. The leadership's demonstrated here. CSU is leading the team, but JPL is, of course, leading the implementation side of it. They're managing the implementation side of it. We have our industry partners for our antenna and the spacecraft. The data center will be done here through CIRA, just as it was for CloudSat. Phil Patain's leading that. We have an extensive science co-Is, and each of these co-Is represents a huge team. So just to be clear, these were just the co-Is on the proposal. We have 5 universities involved, 3 NASA labs, NOAA's involved. We now have more than 20 postdocs and early career scientists, and we've got a student collaboration coming up involving 10 students. And then we have a lot of international collaborators. I'm sure most of you recognize this guy, but there's a lot of people from England, India, France, the WMO, and so on. So 8 international partners in 5 different countries. And then we also have an advisory board, and if you're a convective expert, I'm sure you recognize all of the names on this list. So we're very grateful for the contributions of all these people. They represent a wide range of skills and expertise, from modeling all the way through remote sensing, radar, and so on. And so I'll conclude there just by finishing with this slide. In essence, the INCUS mission will provide us with the first tropics-wide investigation of this evolution of the vertical transport of air in storms within convective storms. And this is arguably one of the most influential and yet unmeasured atmospheric processes. And if you want to learn more about us, the webpage is up and running, and we keep it fairly active. And so with that, I'll stop. Thanks very much for your time.
Thank you very much, Sue. So questions, maybe I start with one. So your science objective 1, right? You define this link with the environment. So what is the environment of a storm? It's more a philosophical question. What kind of spatial variability, spatial scales are you talking about? Which variables are you thinking about?
Yeah, Alessandro, that's a brilliant question. And this is a question that has kept us very busy over the last 3 or 4 months, because as convective people, in essence, you have to ask the question, what is the storm reach, right? How far out do you have to go from a storm before the environment is meaningless? And so we've been doing a lot of work in that regard, looking at how it scales away from updrafts. And then, of course, you've got the problem with isolated updrafts versus organized updrafts, right? Do we have to worry about the local environment around multiple updrafts within a large system? So there's a very much of a localized environment for those updrafts versus more of a storm scale environment. And even the storm scale environments, I would argue that as a convection community, we've got a lot to learn about what that extent is. If you drew an updraft, can we draw an environment 10 kilometers away? Is that enough? 20 kilometers radius away, is that enough? Is it 50? Is it 100? So we're doing a lot of statistical assessment of that right now. Of course, the environmental data that we will be using with INCUS is typically ERA or ERA, the ERA observations. And so we're looking to see whether from these high resolution simulations on 100 meters, how much of the variability we miss with ERA, right? Both spatially and temporally, and how much that'll affect our results in assessing the science objective 1. So it's an excellent question, and a lot of work is going into it right now.
Okay, thank you very much. Maybe I have another one. So why the models, they have more uncertainties in the eyes than in the, just maybe a stupid question, but just why is there more uncertainties there just for the microphysics, or I don't know?
Yeah, not a stupid question at all. It all comes back to the microphysics. And it's, I think in part, and people often ask me, because as you know, Alessandra, I'm a modeler. People often ask me, what's the most challenging thing in models right now? And it's high resolution models, to be clear. And I would argue the ice phase and land surface processes. Ice phase is so challenging because ice, as you well know, comes in multiple forms. And we don't know a lot about that theoretically. For example, secondary ice processes. We still got a lot to learn on that. We still got a lot to learn on the processes of rhyming. There's multiple phases involved. So we really can only represent in our models what we understand theoretically. And I think we've got a long way to go in understanding ice processes theoretically. And of course, that then feeds back to the updrafts by virtue of phase changes, latent heat, condensate loading, and so on. So, yeah.
Thanks a lot. So, any other from the audience? Otherwise, I think thank you very much again, Sue, for your very interesting talk, and thank you very much for waking up so early.
Thanks so much, Alessandra.
Yeah, we'll see each other. Okay. Thanks a lot. Okay. So we have now the third talk of the session, and I think this is a recorded talk, unfortunately. So the speaker is Francesco Battaglioli from the European Severe Storms Laboratory in Germany. And then I think we can start the recording.
Good afternoon, everyone. I'm Francesco Battaglioli from the European Severe Storms Laboratory, and I would like to start by thanking the organizing committee for this invitation. Unfortunately, I cannot be there with you in presence, but yeah, nonetheless, let's start with the presentation. Today I'm going to talk to you about the application of our logistic models to reconstruct the climatology and the long-term trends of large and very large hail, but also to improve the forecasting of these events. Now, you may see from the title that we use these RCHAMO models, and you may wonder, what does this stand for? Well, RCHAMO stands for Additive Regressive Convective Hazard Models. You're not expected to remember the whole name, but the important thing is remembering that we model large hail by taking convective initiation explicitly into account. And what do we mean by this? Well, we do have a model that outputs the probability of having a storm, so the probability of having convective initiation. Then we have a second model that outputs the probability of having hail, given that we have a storm. Take the product probability of these two terms, and you obtain the overall probability of large hail. Now, how do we train these models? We use three different data sources: lightning observations from ATDNet, hail reports from the European Severe Weather Database, and convective parameters from the ERA5 reanalysis. Now, the first step to model large hail is understanding what are the conditions that favor it. And we can do so by showing a 2D histogram, which displays how the relative frequency of large hail to any thunderstorms varies depending two atmospheric predictors. On the y-axis, we have the deep layer shear, and on the x-axis, we have a form of instability, in this case, the theoretical updraft wind speed based on CAPE. Increasing instability, increasing shear, increasing probability of large hail. Now, what do we do effectively with our models is fitting a probability field that is smooth now and reflects the observation. So now for any single combination of deep layer shear and Wmax, we have a probability of large hail. And with this so-called lookup table, we can apply it back to the reanalysis, assigning to any grid box to any time step throughout the 72 years of their analysis for the whole of Europe a probability of large hail. And if we integrate throughout these 72 years, we obtain an objective climatology of large hail. Now, we do this for Europe, but we can also do it for the United States. Now, I'm not going to spend too much time on this, but I just want you to focus on the fact that this is not our final model. We employ four-dimensional models at the later stage, and I want you to get how we got there. So now I'm going to move to the model selection procedure for these RCHAMO models. Now, it's important to realize that we have about 140 predictor parameters, potential predictor parameters from the ERA5. So we really cannot test every possible combination of these potential predictors. So we use our physical understanding of large hail to streamline the procedure a bit. So we know that for large hail it is important to have instability and shear. So what we do effectively is splitting these predictors, these potential predictors, into three main categories. We have thermodynamic related predictors, we have shear related predictors, and then we have other predictors, for instance, the height of the melting layer or the height of the cloud base, that literature tells us, okay, these parameters are also important for large, so we test them as well. Now we start by developing a two-dimensional model based on the combination of the thermodynamic and the shear-related parameters that yield the highest scale. So now we have a two-dimensional model, and we make things more complicated by adding a third predictor within this category, this other category, and we add the predictor that adds the most scale to the initial two-dimensional model. Now we iterate this process and we go to 4 dimensions generally. This is when the model starts overfitting. These are our final predictors for the large and the very large hail model. So for large, I mean larger than 2 centimeters. For very large, I mean larger than 5 centimeters. And you see that 3 out of 4 of these predictors are shared between the two models. The only difference is the height of the melting layer has been chosen for the large hail, so for the marginally large hail, while the height of the cloud base has been chosen for the very large hail model. This is also reflective of our physical understanding of the 2 different sizes of hail. Okay, so now we have our predictors, we have our models. As I anticipated you beforehand, we can derive a climatology that is objective. And the important thing about these maps is that they're not influenced by any non-meteorological factors such as hail reporting density or population density and so on. These maps are objective and reflect the probability of large hail based on predictors of large hail. So on the left you have a hail of 2 and on the right hail of 5 centimeters, and you see that the distribution and the hotspots are similar. You may notice that northern Italy is one of the hotspots of the continent, but we also have southwestern France, eastern Spain, and yes, also northern Africa. I mean, across this region we don't generally get many reports, but when we get them, they are generally concerning giant hail. I remember a report from Algeria or Libya where there were like 17 centimeters hailstones, so something clearly remarkable. Yes, so this is for Europe. We can also do the same thing for the United States, hail of 2 and hail of 5 again, and we can see that we have this hotspot across the central plains that for the very large hail size moves more towards the Rocky Mountains. This is also in agreement with local climatologists. But the important thing and the cool thing about this model is that we can really draw comparisons between regions, because the models for the US have been developed using the same exact predictors as for Europe. So if we take the maximum across the United States, say this region across Kansas, Nebraska, and Colorado, we can say that large hail in this region, the US maxima, is about 3 times more likely, climatologically speaking, than in the European maxima, northern Italy. Okay, so this was the climatology. Now we have about 72 years of data, so it would be a waste of data not to look at trends. We try to answer the question, is hail becoming more likely across Europe because of climate change? And the answer is yes, broadly yes. There is, we find positive and significant increases across large parts of Europe, especially Central Europe. We have France, we have Austria, we have Italy especially, And you see that I'm highlighting this region across the Po Valley and northern Italy in general, not just because we are presenting in Bologna or because I'm Italian, but really because this is the region where the largest hail increases are modeled according to our channel. And I want you to visualize this increase. We can visualize this increase using these so-called hail stripes. Of course, you may have seen these climate stripes, these warming stripes from Ed Hawkins, University of Reading, where it shows the increase of temperatures with time. We're basically applying this concept to large hail. So effectively what you're seeing is every stripe is representing a single year. Years in blue are below average, years in red are above average. And if you take a specific year, say 2018, we can tell from this graph, okay, this year was about 100% above the average, the 72 years average for large hail, and it was about 200% above average for very large hail. And we can also do a bit of statistics to work out that if we compare the first 10 years of the time series with the last 10 years of the time series, of course, these are not climatological comparisons, but we can say that hail, very large hail especially, is now 3 times more likely in northern Italy than it was in the 1950s. So a very abrupt increase. Okay, so this is for northern Italy in terms of increase in frequency. What about the seasonality? Is climate change resulting also in changes in the seasonality of hail and lightning across the region? Well, we can check, we did check, and here we are plotting the model seasonal cycle for 3 different periods, 1950 to 1973, 1974 to 97, and 98 to 2021. And yeah, if we focus especially on hail, which is the main topic of the presentation, we can see how the red curve especially is very skewed towards the left, so towards earlier months. And especially if we quantify this increase, we can say that May is the month with the highest percentual increase, and we can really conclude that there is a tendency for these events to start earlier during the year. Okay, so up until now we looked at Europe. Now we check across the United States to see if such strong and positive trends as we saw in Europe are also present in this region. So from these maps we see that the trends are much more localized and comparatively small. There are regions with significant and positive increases, such as southern Canada, but also parts of Colorado, but there are also areas with significant and negative decreases. So the pattern that we saw over Europe with a widespread positive trend is actually not present in the United States as well. The next step in our research was to develop a global hail model. To do so, we joined forces, so we developed models using hail reports from Europe, the United States and Australia all together, and same thing for lightning observations. So we end up with about 45,000 large hail reports and 5 million lightning observations to train our model with. What do we end up with when we apply these models globally? This is a yearly distribution map of model very large hail. And we see several regions standing out, for instance, the Northern Great Plains, the Mendoza region in Argentina, but also South Africa as well as parts of Central Africa and Asia. If you look across Europe, we see a high internal variability, but if you focus especially over the recent years, and specifically 22, we see how the distribution is high compared to the other areas. And really, we see that the brightest colors for the year 2022 are found in France, in Spain, and northern Italy. This suggests that in 2022, eastern Spain, France, and northern Italy were the global hail hotspots. So there was no other region in the globe where our model indicated a higher frequency of very large hail compared to Europe. But how does this compare to the climatology? For instance, if we take France, year 2022 was about 216% above the 30-year average from 1992 to 2022. If you take northern Italy, this value goes down, but still stays pretty high for, relatively speaking, as a 135%. Now, this is the model output. One may wonder, okay, but was there really so much hail in Europe in 2022? Well, the answer is yes. 2022, according to the European Severe Weather Database, was the year where we recorded the highest number of reports of very large hail. So about 80 days with very large hail in 2022. Okay, so the last question that we want to answer using our climatological application of their channel models is large hail becoming more likely because of climate change globally? Well, you already see a lot of blues in this map that indicate negative decreases, especially across South America, Central Africa, but also Southern China, parts of Australia, as well as parts of the United States. And really, like if you plot these stripes for several regions, Norman, Oklahoma, Mendoza, Argentina, Guangzhou, China, and Venice, Italy, we really see that the only stripe that is going from blue towards reds is actually the Italian one. So we really see that the increases in Central Europe, especially Northern Italy, are extremely specific in a global sense. Most of the globe is experiencing a downward trend in large hail environments, especially in South America and Africa. Now, I showed you a lot about climatology and trends. Now, I want to focus for a bit on the potential for forecasting applications of these channel models. And now I'm going to show you a video from the 18th of August 2022, when a derecho formed across Corsica, moved across the center north of Italy and all the way to Austria. And this is a video taken from Rapallo, in Liguria region. And yes, I will let the image speak for themselves. So I will stop the video, otherwise probably gets too loud. But yeah, this is what you can see towards the end of the video. Wind-driven, very large hail. That's what was falling over the port. And yeah, so this was an extreme event that affected most of the Mediterranean basin. I mean, Central Mediterranean, Italy. I told you even up to Austria. But the question that we can ask ourselves, are we able with these logistic models to forecast these events? And this indeed is something that we do now operationally. We have this website called Storm Forecast EU, where we daily, we have this algorithm that outputs a daily probability, a daily forecast of lightning and large and very large hail for the whole of Europe. The website is publicly available, so you're welcome to go and check it out. But this is an example from the 18th of August. So our model is telling us that over Toscana we had about 80% probability of large hail, so these orange colors, and we had about 40% probability of very large hail. So these contours, these thick and wide contours. So this is the hail forecast for the day. You see that there are also other regions where we had a high hail probability. But how did the forecast verify. We can overlay the hail reports for the day on the forecast, and we can really see that these green triangles, the hail reports, really fit well with the forecast, with a bullseye across Toscana. But if we move to other regions, the Caucasus mountains, or also towards Spain, we see that the hail reports fit very well with the hail forecast. So we were this example shows that Archamo has some potential also for forecasting in the short and in the medium range these events. Okay, so now a few key takeaways. We talked a lot about climatology, a bit less about forecasting, but yes, so what questions can we answer after this presentation? What are the European hotspots of large hail? These are the Po Valley in northern Italy, eastern Spain, and southwestern France. Is large hail in Europe becoming more likely because of climate change? Yes, there are broad regions where hail is becoming more likely, and especially northern Italy is the area to watch out for. So here we have a threefold increase compared to the 1950s. Now we go more towards a global perspective. What are the hotspots of large hail globally? These are the Great Plains in the United States, the Mendoza region in Argentina, South Africa. I had also parts of Asia, and recently also Europe. Now, in terms of trends, is large hail becoming more likely because of climate change globally? No, the only region where hail is modeled to have become more likely is actually Europe. And finally, I introduce you to Storm Forecast EU, which is our website, publicly available. Please check it out if you want, where you can check our forecasts of large, very large, and very large hail and lightning for now up to 2 days in advance. And with this, I will conclude. Unfortunately, I'm not able to take your questions, but please, if you have questions, contact me via email or Twitter, and I would be more than happy to reply to you. With this, I thank you once again. I thank you, the organizing committee, and I wish you a good continuation of the conference. Thank you again.
Okay, we can thank Francesco. Okay, given its doom prediction for Northern Italy, I genuinely hope that he's wrong. But anyhow, any comments on, or some final comments on this talk, or do you want to say something? Any climatology that can confirm this from our radars? I guess it's difficult. Was 2022 really that bad in terms of hail here in Northern Italy? Anyhow, no. I mean, it seems that it's so a clear signal at least in the environment that is driving to hailstorms that maybe, well, model. Any other comment? Otherwise, I think we are ready for a coffee break, and then we resume operation with Zernich Dusan in half an hour. Okay, thank you, everybody.
Should I start now or wait a few seconds?
Yes.
Yeah, of course.
Okay, Luca. Solito casinista.
Siediti. Is that how you say, sit down, how do you say?
No, siediti era imperative.
Oh, no.
Sit down.
No, polite way is say delay.
Prendi
la posizione.
Okay, so I think we can start the second international session. And I think everybody knows Dusan, has been with us these past 2 days.
Yeah.
So we're not...
A long time.
Yes, well, of course.
Viejo.
Yes, apart from the 2 days, of course. We know him from other things. So anyhow, the floor is yours.
Thank you. Can you hear me? All right. Let me start a little bit with some administrative things and so forth. I work for the National Severe Storms Laboratory, which is part of Ocean and Atmospheric Research, which is part of NOAA. NOAA is the agency, and NOAA is under the Department of Commerce or Ministry of Commerce. So we are the research arm for the Weather Service. Weather Service is also part of NOAA. So we develop technologies for the fairly, let's say 10 to 20 years, hopefully, applications. Now, this is the topics that I will be talking about some principles about phased radar, volume coverage, speed, rapid observations, benefits of PARs here and there, dual polarization of PAR, very important, and then about few PARs that exist that are being researched. I have put my name here, and for more information, if you want about details of some of this stuff, you can Google NSSL publications reports. If you do that, you'll find out some reports that are not being published in the open literature. And my email is down there, and I respond, I answer, I have answer as a PhD, answers to all questions with no guarantees that are correct. Okay, now let's look at this benefit versus year of technology. And I drew this kind of diagram without the power. And what it means is, at the beginning, let's look at the radar effectivity. At the beginning, in the 40s, effectivity radar was discovered, and people found out that it can see through storms. But initially, during this research, you start learning things that you couldn't do from other instruments, and then maybe you can understand the phenomena even without the instrument effectivity because of the understanding that you learn. Then at the time of implementation, there is a rapid increase in benefits, in operational benefits. There are two things. First, it has to be spread you have to cover the whole country one by one. Then people have to learn, and they still have to learn more, and then you reach a plateau, and then the benefits are reaching, saturation. Well, the one thing that is wrong, in my opinion, I drew here a Doppler benefit larger than polarization. Really, I think that the polarization provides more benefits, more useful globally, but I don't want to discuss that too much. Phased array radar is another little step, maybe a little bit smaller step, because it can provide faster and better data quality, but new information, not so much of a new information. Well, let's go then to show you the example of what I mean by this curve. Incidentally, when I drew this curve, it came out from my mind, I kind of made it up. But then I looked, and the papers, people have written papers about this S-curve, and they wrote, dissertations. So anyway, this is an example of the lead time in minutes, and here is the years next ad implementation between 93 and 97. So lead time in minutes of flash flood services. Look, it starts increasing just when the radar is being deployed, and then boom, it reaches a plateau. It's a next-ad radar. It's not because of the Doppler, but because of the quality of the data, digital, and all of these other things. So this is just to give you an example that these things exactly, pretty much mimic what the theory would say. Now, this is a little bit of almost of a joke, but let's say, what is the difference between a phased array radar PAR and the conventional radar? The PAR is blue, conventional radar is white. Well, explanation. In this dome was white too. When we painted it and we put the radar there was a lot of complaints in Norman. Residents didn't like it around. What is it? Why is it blue? It ruins our neighborhood. Well, let's see. Joke aside, National Radar Single Polarization PAR was inside this radome until 2015. Then in 2017 to present, we have put a new phased array radar dual polarization. And I will talk about that a little bit. So it's in this dome, and we started getting data 2020. Maybe it takes a long time, you know, as I said, much longer than you anticipate. This radar here is the WSIAT, and belongs to NSSL. Actually, another story, I went to Washington to beg for the radar, and we got this, we made some trades, and that is, on that one we made the modifications for dual polarization, and my office was here in that corner, and I spent my maybe most productive years there working on this stuff to make it happen. So anyway, let's give you an example, an explanation of how the phase array works, what's the principle. Imagine you have a flat surface and you have two little balls, and you start vibrating at the same time, these two little balls like this, and you create waves. The waves spread in circular paths and propagate, and over there in the middle, they add in phase, and you have like a focusing to the middle. Now imagine a slightly different situation. Say that you have 5 persons on a riva de mare. 1, 2, 3, 4, 5, each has a stone. This one here throws the stone, then this one throws 1 second later a stone. The 5th one throws 5 seconds later a stone. By the time this has thrown the stone and it starts making the wave, it's a small circle. This one, big circle. The tangent on that, the wavefront then would be moving that way. The waves would add constructively in this direction. And that is the essence of the phase array. So now this is your phase array explanation, as we would say 101 in the United States. Now, did you know that there are more weather phase array radars than the total of all weather radars? Aha. What kind are these? On airplanes, these flat plates are actually phase array. They have sources. Each little hole is a source, and they're all in phase. So you cannot electronically control them, but you turn this antenna, but they're all in phase and always shining perpendicular. So that is a phase array, actually, principle of the phase array. Anyway, that was something to just get you maybe interested. Now, fast volume updates. The fact is that for singles, we had a single radial, and it doesn't matter if it's a phase array or whatever radar it is, you are limited by the decorrelation time, by number of pulses, so there is no benefit in, there's no magic. But the phase array can do certain other things to get around this. And there is beam agility in pointing direction and in many other ways that phase array can achieve much faster update rates. For example, if you have 4 phases, because you know if you have one phase, then you can scan this way. But what about the other? If you have 4 phases, you could transmit 4 beams. So that would be a way to gain. And adaptive scanning and so forth. So I'll discuss some of the things by which this can be achieved. For example, on this, I show focusing. Focusing really means we are concentrating on a certain area and scanning right there and ignoring the rest. So we can do very fast because there is no inertia. There's no inertia of the beam. We don't do this. Now, there can be space-time multiplexing. I can send 4 beams in 4 different directions and scan sweep like this. These beams can be in one pulse, one next to the other, because we can shift very fast the phases. So those are the possibilities. Another possibility is you transmit a very wide beam. On receive, you transmit a wide, and on receive, you synthesize beams in these different directions. So wide here, and many you receive. Of course, there is lots of sensitivity. There's always some kind of a trade-off, but the phase array allows you to do these things. And this is the example, for example, that I'm talking. Suppose I have a pulse that's pointing at minus 30 degrees, 30, 0 and 30 degrees. In other words, during this pulse, this is 1 microsecond, maybe half a microsecond, whatever. And I can focus, and the phase array doesn't move. I can focus there, so the first part of the pulse is there. The next part of the pulse is 0. The next part of this pulse is 30 degrees. So in this very short pulse, which may be, I don't know, 1.5 microsecond, I have gone into 3 directions. Of course, I need power, so in that regards, I can gain in. Now, of course, we can put the phased array antenna on the rotator platform and rotate, and that's another realization that's finding applications. Here I'm showing an adaptive scanning that's from Sebastian Torres. Some of our guys did this, and they actually programmed it. Through the lower elevations, you do some surveillance scans once in a while, and where you see storms, you scan just through the storms, and you don't waste your time in empty space. So that is also a way to gain some speed. Examples of rapid observations, I will show you some examples, and you will see it's pretty and obviously should be more useful. Now, the first one of that I will show example was this National Weather Radar testbed. It was a phased array that was removed. It had only vertical polarization. It had 1 transmitter, but you could change the phase on transmission. You had waveguides and analog shifters, so you could do that. And Research Nextrat, I will show data from Research Nextrat, the one on the tower, KOUN at NSSL. Oklahoma City operational radar called KTLX, which is 20 kilometers away. And I'll show some data from the rapid scan radar that University of Oklahoma has, but that's not a phased radar, but just very rapid scan to show you the pretty image and the possible use of these rapid scan radars. Now this is the phased array radar from 2011, and the tornado, you see this green and is along the propagation path, and you see nice continuous observation, whereas this one here is the KTLX. It jumps because it's every 5 minutes or so. So it's obviously you can maybe assimilate better, and I'll show that you do. So that's one example. I'll show you another example of a tropical storm, Erin, that came over Oklahoma. And this is at about 40 seconds time update of this lowest elevation, whereas on the KTLX, which is 20 kilometers away, it's about 4.5 minutes. So obviously we can see and we can capture more of the rotation. Maybe the model will do that likewise, but if I have all of this data, you would expect that I will be able to better predict or better use it in a model. I do have also the PAR cross-section. This is images are taken every 26 seconds in the RHI, and here it is the same, but every 5 minutes. Same data, but every 5 minutes. Now notice there is this 3-body scattering. This is the coming from this, and it comes down. You see the core is here, and there is the signature, and it comes down, and this behind comes down. So you can see this evolution much faster than, or you can capture it much more quickly than otherwise. Now I will show you the data that was obtained every 5 seconds in the RHI, but again, it is a conventional radar that Pro-Sensing, Andy Pasmani and his group built. So there are some tricks to do that. I don't want to go into that, but every 5 seconds, and pay attention to this place where the KDP changes. So it's about 10 minutes. So you see, you look at it, and all of a sudden, hop, it disappeared. Well, what happened? Lightning discharge. The particles are oriented. When the lightning discharges, they get disoriented, then it builds up. So these kind of studies, some of my colleagues intend to do, and they have actually received an NSF grant, but a small one, small, maybe a few $100,000. They would like to ask for a big one, but that's in the plans. Okay, let's see what else. Well, in the ordinary thunderstorms, this is a sketch from the Lincoln Lab, maybe a up and down thunderstorms that may last 35 minutes. Actually, the images here down are at every 3 minutes. So you can see a rather big, quick evolution. And if you're sampling sparsely, you're going to miss it. You may miss the flash flood warnings or whatever to the observation. a study was made by humans. They looked at, humans were analyzing the data, and they had 17 cases of microbursts. And with the sampling at the 1 minute interval, and the humans did this now analysis, sampling at 1 minute interval, they discovered precursors in 14 out of the 17 cases. They were able to tell, this is going to produce the microburst. When the update was reduced to increase, the update time was increased, the time was increased, but the sampling was, well, time between, reduced, so that at every 4.4 minute update, only in 11 cases they were able to see the precursors. And the median lead time to detection was about 9.5 to 10 minutes, whereas over here it was only 5 minutes. So this is a type of study that kind of justifies and is shown or published so that we continue this research. Another study was from Yusuf Estensrud, in which they simulated the storm, and then it's all simulations. Then they sampled it at 1 minute interval, 15 samples or 16, and every 16 samples, and every fourth sample. So if they did it like every minute, which would be like phased array, this is what you'd obtain in terms of effectivity, and this is the truth, assimilated at the end. So the truth in the effectivity is they agree very much. But if it was done at every fourth or much less often, this is not as close to the truth as this one in effectivity. And also the velocity, intensity of the velocities, vertical velocities, the quick sampling and the truth agree quite well in place and intensity, but the one that was sampled less often does not. Another example that was done on actual data, not simulation, was in 30 minutes of assimilated data, one from the NWRT and one from the WS80AD. And in case of this NWRT assimilation, the location, the probability of rotation are these contours, these in color, and this black kind of wiggly contour is the location of shear determined from the MRMS system, the radial shear. Now you can see that the agreement between that shear and this from the NWRT assimilation is much better, well, considerably better, I don't know how much, than in the case that you would have a W7 minute update assimilation. So this is on the actual data. Another thing, now this is something that the phase array can do easily. I'll try to explain. Imagine that you're sending a wide beam that's between -90 and +90 degrees, wide beam. And then you receive everything else, and then you're looking and looking at and doing the spectral analysis at -90, at -89, at everywhere you're doing these spectral analysis. So you're plotting the azimuths here on the vertical axis and the Doppler on the horizontal. Now you would not do this between plus and -90. You would do probably between -10 and +10. So if you do this analysis and you have, this is a simulation, and you have a windmill, let's see what we say. This is due to the rotation. As I'm observing this between -10 and +10 degrees, I'm looking at the spectra, I see this is due to the blade rotation. As I'm going quickly, I see how this blade is rotating. This part here kind of is really due to this, to the post. Now, this is 40 dB of turbine to weather signal. When I remove this turbine, and this is what I've removed, here's the weather signal. You cannot even see it. Here's the weather signal. So really, you can imagine that we would have something like this window. We'll be able to remove this, and we'll be able to get the weather signal in the presence of wind turbine. This is not really possible with a conventional radar, or very difficult. Multi-mission capability of power, this is a cartoon that we put. The idea was to use the weather radar both for aircraft traffic, for homeland security, and for several purposes, but it turned out that what motivated this partly. First, it could be done. Second, there are air route surveillance radars, 1,350 megahertz bandwidth. They are around the states, and they also have a weather channel, but they are to look at airplanes. The Congress mandated or take them out. Your children who play with these telephones and stuff like this, they want more bandwidth. So the Congress people's children also want more bandwidth. So the government says we are selling 50 megahertz for $20 billion. But what are we going to do with these L-band radars? Get them out. So the idea was to maybe combine these with weather, and that was under a program called Spectrum Efficient National Radar System, sensor. NOAA was part of it. I was kind of part of it. But the thing had to be done by 2024. After 2024, these radars are going to go out. So the new ones would have to, FAA has to do something. NOAA, without weather service actually, decided it was premature. They could not commit. They didn't believe that, and they were correct. They didn't believe that the industry is ready and ripe to do that on such a short time scale. So NOAA is out of this, but Air Weather Service and FAA and Homeland Security, they have to worry about that. So there is no more talk about multi-mission. Although if the phase A becomes operational weather services, it could be doing the multi-mission. Now, the most important part for me and others is dual polarization on the PARS. And I will show here some far field orientations from radiators. I'll be talking about beam cross-sections, some issues in calibration, dual pole PARS. So I don't have really much here, but I'll try to convey some physical principle what happens. If you have like little antenna dipole, like this, and it oscillates, electric field oscillates this way, and you look in a far field, the lines of the fields are this here. This vertical dipole produces the lines like a meridian on a globe. So this is the orientation. Straight here, the electric field will be oscillating like this, but it will be oscillating like this, right? But over here, it will be oscillating like this. So it will not be, you understand what I mean? It will be tilted somewhat. We accept tilt in this plane is kind of okay. But tilting to the left and right creates couplings between H and V. Because the H component, you twist, you turn this globe and the meridian is here. So the H component is, the orientation are these other. And if you look at the angle between these two components, they are not anymore 90 degrees. They are 90 degrees only in this principal plane and in this principal plane. So there is a difficulty. Now, very similar thing happens with the patch radiator, which is like a magnetic dipole. In that case, the electric fields are like parallels. So you have parallels like this, and you turn them around, parallels like this, but they also are not orthogonal. What you would like to have is meridians and parallels. That's difficult. So that's possible. Meridians and parallels are possible if you create a magnetic and electric dipole. But we had an antenna that we tested, played somebody, but that's a three-dimensional structure. It's very immature technology. So anyway, there's just something to call out your attention. Now this here shows you, in case of an electric field from the Hertzian dipole, the orientation. That's just like previous picture. Now, what about some geometries and some other stuff that was going on in Oklahoma. One way to avoid this orthogonality problem is a cylindrical array. In a cylindrical array, if you scan perpendicularly to the cylinder, you would have the two, because it's a principal plane, they'll be always orthogonal. Now, if you commutate, in other words, you jump and you have all the change in the phase, and you change like this, you will again be orthogonal. So with a cylindrical array, you maintain the orthogonality, but the magnitude will change, but they'll be orthogonal. Now, with the planar array, the principal planes are perpendicular to the red lines, so you're orthogonal only in these two principal planes. So the University of Oklahoma has built this, both of those actually, and they are now in the process of testing and working on this one as we speak, sort of. So this is most important. This issue has been killing the contractors and others, and it took me a few years to really figure it all out and understand the intricacy. Now, if you have a phase array like this, actually what I drew would be like a circular aperture. If you have a circular phase array, if you scan in a principal plane, the beam cross-section here would be the smallest. Then as you go up, the beam gets wider and wider this way, it becomes like an ellipse. But if you scan in the other direction, it does the same thing. So you have these changes of the beam shape. So you have also to account you have to take account of this with your geometry. With a cylindrical array, you don't have this problem. I mean, you have the problem that in this plane, the beam width changes, but next, if you commute, it's the same change. So you have, in this one, cylindrical, you have one order of magnitude less complications. Here you have an order of magnitude more. Every point is different. All right, so here is the actual beam cross-section, main beam and side lobes, where the pattern at a 20 degrees elevation and 40 degrees in azimuth of a planar array. So it shows, computation. Over this here is a cartoon, right here, something like this. But here is actually computed. So issues affecting duopolarization data, coupling between the horizontal and the vertical components due to geometry. That's what I showed you, this coupling. We want H and V, because H and V are decoupled, bigger due to gravity, larger drops. But if you are coupled, then there is more difficulty. It's hard to unravel and figure out what's going on. Cross-polar patterns present in PAR and conventional radar. You have a cross-polar pattern. Matching of beams at vertical and horizontal polarization. You have to have that. They are present in both conventional and PAR. But this coupling is really present, geometrical coupling only in PAR. Calibration enables quantitative measurements of polarimetric variables. For conventional radars, I told Alessandro, only two equations. Z equals some kind of a radar constant, SNR, and minus 20 log R. That's it. You have to, and it's not easy. It's still most difficult to get this absolute C sub Z, very difficult. With ZDR, you also have one. You have this C of ZDR for conventional radar. And then you have this 10 log of PHP, but you have to, to calibrate that. Now, it involves determination of the radar constants C, Z, and CZDR. For the planar phased array radar, it involves solving three equations that are coupled. Remember, we had over there something. I had power at H, I have power at V, they are coupled, and I have a cross product, H times V correlation. Three equations to solve to get. These are simple equations, but you don't know the coefficients. When we have so much difficulty getting this C sub Z, when I have three equations, they're all coupled and very, very hard. All right, so I'm very close to finishing. The advanced technology demonstrates that that's a 10 centimeter wavelength that the Lincoln Lab has built. It is in this, and here is its antenna, and it consists of 76 panels. Each panel has 64 radiating elements, 64 patches. So we have a whole bunch, 4,864 radiating elements, but then the panels are combined into subarrays. So really we digitize 24 streams of H and 24 streams of channels of V polarization, 24. So it's not fully digital because it takes part of the arrays and digitizes, sums it and then digitizes. So, and here would be, you see, these are the number, these dots is where we get the signals. If you count out, there's 24 of these, and the panels are there, so this is a schematic of this that, as I speak of, is being investigated. We do have a calibration tower over here, trying with a keyboard, trying to calibrate that, and we turn and calibrate precisely to solve this ungodly problem that I was just talking on the previous slide. Bias in Z versus azimuth, 0 elevation, and if I switch with azimuth, the ZDR bias due to beam skinny, look, there's no bias and it gets to be 2 to 3 dB at minus 45 degrees, and pretty much you'll be scanning plus minus 45. Well, you have to measure that, you have to take that out. And this is in the principal plane. Now if I go out of the principal plane, then I have more difficulties. And this is the differential phase that changes 0 to minus 50 or so degrees. And that is not so serious because we can estimate differential phase from the returns the closest to the radar returns from rain. Now I'll show you some example. Advanced technology demonstrator, that's that radar, and KTLX, which is 30 kilometers away, and very, very nice Z, they look very reasonable, and the ZDR, very reasonable and smooth. Now, to be honest, this is a little bit misleading. This is not so nice because of the phase array. It's nice because we sample at 37.5 meters. We oversample. Over here it's sampled every 250 meters. Over here we are sampling it much more often and then smoothing. So I need to be honest, this is not a feature of the phase array. This is a feature of this specific processing. But still, very reasonable. I mean, if you look at this and you look at this, you say, gee whiz, this really works. At 2.1 degrees elevation, not too far of the principal plane, there is hope. There is hope. Now, this was on one day, and we compare 1.8 with 2.1 because this one is, KTLX is further. So, and this one is closer, so they will be pretty much at the same height, roughly. This is another day where we compare them at 1.8 degrees, KDP. Again, very reasonable. If you look at this and this, you would say, maybe it's the same. Another Horus, I want to mention about Horus. This is, I already told you about that. It is also 10 centimeter wavelength, but 2.6 degree beam width with no taper. But they have to taper it and do something so the beam width is reduced. But this is a learning process for them. This is fully digital. Every element is digitized. Signal from every radiating patch is digitized. So you have 1,600 eyes of H, IQ of H, and the same IQ of V. So there's a lot of boku of data. And here is data from the partially populated Horus. And you look, and this is, actually this looks to me very, very nice because they had only one column. So they had like 12 degrees, or I don't know how many degrees wide azimuth. They had a narrower beam in elevation. And they scanned, and it looks very reasonable. If you look at this, fairly reasonable. Although, you know, in a rowan tree, I don't know where it's melting, but overall looks very encouraging. And okay, this is actually the phase array, but as I said, only one column because they didn't put the other ones in. This was in the spring. Now they've got most of it. Advantages of all digital power. Some of these features make a powerful radar. fast update rates, but instantaneous retrieval of transverse winds. I don't know if it's possible. I put in red what I think may be. And I put here continuous comparison. If you have a radar and you have in situ probe like an aircraft, with the phased array you can constantly move the beam ahead of the aircraft and you can just sample and probe the microphysics ahead of the aircraft. No interpolation or anything, no extra work. Best intrinsic resolution. The phased array, even if it rotates, you can always backscan so that you don't have the beam smearing. Optimum low level coverage. You can graze the horizon. You can have a better ground clutter cancelling because you can shape the beam. You can improve measurement of spectrum width because there's no beam smearing. You can selectively probe and do spectral analysis of interesting stones because you have no inertia. And different receiving beam pattern on receive. This is a very important difference. On receive, at every range gate, I can have a different beam, different shape of the beam. Just think, from here to 100 kilometers, at each on receive, I can change the beam. On transmit, I cannot do that, but on receive, I can because it's all digital. I can just synthesize it to be like this, or whatever I want. So that's an advantage, advantage as a feature. Now, space-time adaptive processing, this is what I just told you about these windmills. Lastly, the NCAR just got funding, about a month ago I heard, 91.8 million to build an airborne part on both sides of this airplane. So this is a sketch. There'll be 2 parts on the side. They'll be scanning pretty much in principal planes. Then they had some other radars. I don't know how much of this they will build. You can look at their website. And I don't know if they know how much they will build. It'll probably cost them more than they think. And epilogue is, this is the basic conclusion. It's a subject of research for weather observation. So that's a good thing. Somebody ought to do it. Some meteorological services, China and Japan, have developed PARs on a rotating platform. Well, in a rotating platform, you have this perpendicular 2 fields. So that is available for commercial use. US Weather Services will finish in 2024 the service life extension of the WS-80AD. That means that radar will be good for another 20 years. But after that, they'll have to do something. But there's not going to be any change before that, I guarantee. No phase there or anything. NOAA NSSL is exploring this technology now on a rotating platform as candidate for replacement. 2040, 45, I don't know. I hope I live to see it, but I hope I live with a good quality of life, very important. Otherwise, what's the point? In 2028, we are committed to get one more, a different one, more closer to the prototype, and the budget roughly about 90 million, same as NCAR. For weather services acceptance, a technology needs to be routine. I indicated that before. Maturity is a necessary condition, but it is not a sufficient condition. Well, at this, I'll close. Am I on time almost?
Yeah, thank you. Thank you very much for this enlightening talk.
Well, I hope you learned some important little pickets from here remains, but anyway.
So, questions for Dusan?
Everything is clear.
So have we given up? So essentially, I mean, the fact that we have this rotating, have we given up on the azimuth? Or do you think there is still hope to get?
Right now, we'd be happy to do this.
Yes.
Well, we have not given up because we have this tower and we would like to make it stationary and scan from plus minus 45 to plus minus to plus 20 degrees. Now, you know, there is something else. This is if it is vertically. But if you tilt it, then you get another component. You see, when you tilt it, then you add complication. You like to tilt it because to go higher up, you know, there is some kind of a sweet spot. When you tilt it a little bit, you get this band that is the least contaminated. You know, when you get it a little bit, so that also enters into consideration. No, we have not given up. These colleagues are working on that, and I say working slowly.
Yeah, Luca.
Thanks for the presentation and a comment. So, United States are investing so much in this technology. There are examples in Japan, in China. In Europe, this technology is not explored. At the best of my knowledge, there are no investment on this.
In Europe, you mean?
In Europe. Are we smarter than you, or because
I wouldn't say smarter. We are equally smart. I think probably you may be wiser. And there's a difference. You may let I don't want to say foolish guys, the guys that have money, let them waste it and figure it out. Then we'll do it. I think you are wiser in that regard. Your resources are maybe a little bit smaller. We owe it to the public to do this research because of this timeline, 2035, 40, something has to be done. Now, having said this, in 1998, the director, Jeff Kimple, who became director maybe a year before, he called me and said, Dusan, I would like something new, something to do, something to carry out, something for 20 years. And I said, Jeff, phased array. Oh, good. Why don't you make a presentation? We are going to have, you know what a retreat is? Retreat, when people get together, go somewhere and discuss. He said, no, we are not going to have a retreat. We don't retreat. We are going to have an advance. We advance. So I had to make a half-an-hour presentation for the whole group. But, you know, it's all orchestrated because the director says, and so that people accept that. And he started going around advocating development and studies. And that's where it started. And it took us many years, from 98 to 2010. In 2010, we got about 10 million. And since that time, about that much a year just for but we didn't spend it all. We went out to do these things. So it's a long-term project, and this is still going on. We have this inertia from that time, but it provided a lot of jobs, a lot of fun projects, and some frustrations as well.
Okay, any other question or comments for Dusan? Yes, Mario.
So I'm not an expert in this field, but I'm wondering if there is some direct limitation when you have the electronically scanning that is quite instantaneous. So I'm thinking about the number of samples that you can average to average out the noise. So I'm expecting...
This is exactly the same. Issues are exactly the same. The thing that allows you to do faster is because of no inertia. For example, you can send a pair of pulses one direction, and then you can send a pair in another direction, and come back to this one after they decorate. So you can sum up these pairs, and that means you do some kind of a beam multiplexing pairwise to get velocity, or one by one to get reflectivity. But you have to do the same amount of basic averaging. Now, the Pasmani's radar, they use 4 different frequencies, you know, in this Raxpol. So they have 4 times more samples in, you know.
Enough power.
Yeah, they have to have enough. You have to have enough power. There always you have power, you have frequency, you have time. All of this comes. The phase array has this ability to do that, to interleave that because of this electronic no inertia of the beam. That's the main advantage. It allows you to plus multiple beams, this and then this, but you pay always something. There is always some trade-off.
Okay, another big thank you, Dusan, for joining the conference in person as well. Okay, so we can move to the next talk of the day. And thank you, Manuel. Is he online? Yes. Manuel Werner from DWD. Yes, thank you for staying longer. We are not that bad. So Manuel Werner, the screen is yours, talking about blending of nowcasting and numerical weather models. Numerical prediction models.
Yeah, thank you very much, and greetings from Germany. So my name is Manuel Werner. I work at the German Weather Service in the Research and Development Department, especially in the radar group. So the talk for today is a bit different. I will be talking about the Symphony project, in which we combine nowcasting and NWP products on the convective scale. So this is a rather large project at DWD with many contributors, and the mastermind behind it and the project leader is Uli Blahak. But unfortunately, Uli could not be here today, and so I'm giving my best to be a good substitute for Uli today. So thank you very much for giving us the opportunity to present about the Symphony project. Symphony is standing for Seamless Integrated Forecasting System. And in my talk, I would like to give you, first of all, the basic idea of Symphony and give some motivation why we started the whole project. And afterwards, we will have a short tour through the main components of Symphony. So the focus is placed a bit on the role of radar data in this project, because this is maybe your basic interest and also mine and my working field. So I will be talking about ensemble nowcasting techniques. I will be talking a little bit about the NWP rapid update cycle we are running and developing. And I will talk about, of course, about the combination of NWP numerical weather prediction models with the nowcasting output. And at the end, we will have a glimpse at some verification plots. Yeah, so this is the basic outline of the talk. Yeah, the motivation: in recent years in Germany, we have had severe flash floods caused by slow-moving cells, severe cells, localized thunderstorms with a lot of damage. And these events have revealed really existing challenges and shortcomings in our forecasting and warning system. For example, today, mostly the warnings are based on deterministic nowcasting techniques and products with a lead time, of course, of not more than 2 hours in advance. And so there's no reliable method to warn beyond and to warn earlier. And the NWP models are currently only used to provide a general outlook for the day, but the precise skill for a specific thunderstorm is rather low, and the trust by the users is low because of the spatial mismatching or the temporal mismatches of the cells simulated by the operational models today. And moreover, there have been some issues in the provision of the forecast information along the value chain downwards to the users. Yeah, moreover, our warnings are mostly produced by hand, manual warnings by our forecasters on duty. But the DWD has decided to renew its warning system within the next 10 years. DWD has launched a program called Rainbow, in which the aim is to provide risk-based, application-oriented, customizable, and somehow optimized warning information. And it is also important to provide probability of occurrence for each warning and each event. And in addition, the aim is really to, at the end of the day, reach a fully automated warning process. So this is a bit the background, and in this context, the goal of the Symphony project is to achieve, first of all, better convective forecasts up to 12 hours forecast time. So going from 2 hours to 12 hours. And we would like to develop a seamless probabilistic forecasting system, as I said, based on the combination of nowcasting and numerical weather prediction models. And in the course of the project, we also try to establish a vivid exchange between the users, the DWD forecasters, and also with the flood forecasting centers in Germany. And at the end of the day, these seamless probabilistic forecasts are intended to enter the new warning system. Yeah, so more motivation. Let's suppose we have an x-axis with the lead time and the second axis with some verification score for convective cells, in which 1 is best and 0 is bad. Usually the nowcasting looks like this. You start with a rather good score, close to 1 or even equal to 1. And after short lead time, it's rapidly decaying, because you're usually using some kind of extrapolation and no really modeling of the physics. The NWP takes some time to be produced, takes some time until you really obtain your product, because it has to compute. At the beginning, the score is already a bit lower and then also decays, and there's some intersection point. And around this intersection point in lead time, there's in the products always some kind of discontinuity. So there's no seamless transition between nowcasting forecasts and the NWP forecasts. In our project now, our idea is to shift these scores a bit upwards to improve the nowcasting methods, for example, by incorporating life cycle models, trying to be able to predict also intensification and the decay of precipitation fields, which is always the complicated thing in nowcasting. We also would like to improve the NWP, and then at the end of the day, produce combined products out of the two worlds, which are really as good as these improved individual methods. So we combine and interlock the two worlds. And let me state an important thing. The combination is always done on an ensemble level. So for the NWP, we have already ensemble models, but for the nowcasting, we also intend to develop ensembles in order then to combine the nowcasting ensemble with the NWP ensemble. So everything is done in this setting of ensemble forecasts. Yeah, so to be a bit more precise on the nowcasting side, one thing is we would like to improve the grid-based, optical flow-based precipitation nowcasting. We would like also to improve our object-based nowcasting schemes for convective cells. There's a scheme called Conrad 3D, which I will be talking about in a couple of minutes. And then our task is to newly develop ensemble nowcasting schemes on grids, so in order to predict the aerial precipitation. So this is a method called STEPS DWD, and we're also developing an object-based ensemble nowcasting method called Conrad 3D EPS. On the model side, what we are doing is we are developing a version of our ICANN local area model. The version is that we compute a so-called rapid update cycle, or that we develop a rapid update cycle. So we have a model with hourly updates and forecasts up to 12 hours. Hourly updates, at the moment we have 3-hour updates. And also the modelers are working on an adapted model physics. They are using a 2-moment microphysical scheme in this ICANN RUC. And what is also being investigated and also being done is to assimilate 3D radar data in the model, and also to assimilate the cell objects produced by the nowcasting. And moreover, they are assimilating satellite data and lightning data. Yes, once you have these improvements, you can go ahead and try to combine the nowcasting ensembles and the model ensembles. And in this context, we have 2 schemes. The first scheme is a grid-based scheme called Intense, and the second one is an object-based scheme called Conrad 3D Symphony. And in what follows, I would like to introduce to you a bit the ensemble nowcasting methods, STEPS DWD, grid-based, and the object-based method, Conrad 3D EPS. And then also these combined seamless products, Intense and Conrad 3D Symphony. So the background for all of this is radar data. So here's a sketch of the German radar network to the right. So we have in Germany 17 dual polarization C-band Doppler radars, and we have a 5-minute scan strategy, which is shown on the left. So at the beginning of each of these 5-minute cycles, we perform the so-called precipitation scan, which is a terrain following scan, low elevations, terrain following. And then we perform 10 elevations with fixed elevations, starting at 5.5 degrees, going down to 0.5 in steps of 1 degree. And then after 0.5, we jump up to 8, 12, 17, and 25 degrees. So these 10 elevations have a range of 180 kilometers, and the terrain following precipitation scan has a range of 150 kilometers. So this is basically the radar data scanning pattern. And based on these radar data, the first thing, as I said, I would like to introduce is the STEPS DWD method, which is an aerial grid-based ensemble nowcasting scheme. So maybe to some of you, the STEPS approach is already known. STEPS stands for Short-Term Ensemble Prediction System. It goes back to papers of Seed or Bowler. And this is a scheme to produce ensembles of radar reflectivity or also precipitation fields. And the idea is to use a scale decomposition of the signal and to regard the scale-dependent predictability of precipitation fields, in the sense that the larger scales are clearly longer predictable, and the finer the scale becomes, the more it becomes unpredictable. And the unpredictable scales are, roughly speaking, replaced by some kind of clever noise. And this is done by scale decomposition, Fourier decomposition, and autocorrelation analysis. And by adding this noise, you're able to span some ensemble. We're running 30 ensemble members, and I've shown here 3 of them, and to the right, the observation. And what is also done in this context is that we investigate the use of machine learning techniques to nowcast the intensification and the decay of precipitation, and also to better nowcast slow moving cells or right movers, things like that. So this is the STEPS DWD. And once you have an ensemble, okay, maybe I have to say this is a nowcasting method with a lead time of 2 hours, and it is updated every 5 minutes, and it's running on a spatial grid of 1 times 1 kilometers. And once you have these ensembles, of course, you can compute all these nice follow-ups, like the exceedance probabilities for certain reflectivity thresholds or precipitation sum thresholds. You can compute quantiles, everything, upscale variance, and all the stuff you can also do for the NWP ensembles. Now, once you have an ensemble on the nowcasting side, the question is, how can we combine this with model information? And this is done in the INTENSE method. So INTENSE stands for integration of ensembles of NWP and extrapolation. Extrapolation means nowcasting. So the approach we are running is by a paper of Nerini. And so the INTENSE method produces aerial ensemble forecasts up to 12 hours lead time, as intended, by combining STEPS DWD and the radar reflectivities simulated by our ICON local area model rapid update cycle ensemble. And the question is, how can this be done? How can the blending or this combination, how is it done? Yeah, the approach we are using is an ensemble Kalman filter, in which we take the numerical weather prediction ensemble as measurement. In the context of Kalman filters, you usually have some kind of measurement of a quantity, and you have some kind of prediction model, and you have also the uncertainty for the prediction and the uncertainty of the measurement. And the Kalman filter always combines your expectation, your prediction, with the actual measurement, taking into account the uncertainties of prediction and measurement. So what we do is, we take an ensemble Kalman filter, we predict using our nowcasting ensemble, and then take the ensemble Kalman filter to pull this prediction towards the NWP. Then we do another prediction and pull it again towards the NWP. So the further the lead time goes, the closer we get to the NWP output. So, and this is done for radar reflectivities. So here I have an example. On the left-hand side, you have a nowcasting, one member of the STEPS DWD nowcasting ensemble. You basically see that, yeah, the most of the cells are really shifted to the future. There's some noise on it, but the cells are not vanishing, or new cells are not created. This is not in yet. On the right-hand side, you see a radar reflectivity simulated by our ICON rapid update cycle. So as you can see, the reflectivities from the model look a bit different. So modelers are working hard to get it as similar to the measurements as they can, of course, by refining microphysics and all that stuff. But of course, you see in the model, there are cells decaying, new cells developing. And in the middle now, you have one member of the combination algorithm, and you see some cells really vanishing, and you see also the longer, the further the lead time goes, the closer we get to the right picture. So by this ensemble Kalman filter approach, we can do this combination on the reflectivity level. Yeah, this is the grid-based approach to combine radar reflectivities from nowcasting or measured reflectivities and with model reflectivities. So the question is, how can this be done for object-based methods? This is also something we are investigating, as I said. So the basis for object-based approach, first of all, is the Conrad 3D method. The Conrad 3D is an algorithm that takes as essential input quantity the radar reflectivity from the DWD radar network to detect, analyze convective cells, to track them, and to nowcast them. Basically, Conrad 3D is a deterministic approach, but there's already some stochastics in it because we're using a Kalman filter model for the motion of the cell, or for the cell centroid and the motion of the cell centroid. A classical Kalman filter, not an ensemble Kalman filter. So this is done to track, to smooth the tracks, and also to be able to provide some uncertainty information for the forecasted cell locations. So in this picture on the left, you see some forecast locations. You see some uncertainty ellipses, 1 sigma uncertainty ellipses around the forecast. Yeah.
So, sorry to interrupt. I think for some reason we still see your slide principle of intents.
Oh, okay. I'm sorry.
I don't know.
Is it moving now?
No.
Maybe I can stop the full screen mode and back to the full screen mode. Did something change?
Okay, now we see Symphony, the first, the title,
okay.
Yes.
Okay. So maybe I should go through.
I wanted to interrupt before.
Okay, just no problem. And now, object-based ensemble nowcasting?
Yes, now we are in principle of intents. Okay, keep going. Now, next. Okay, Conrad 3D EPS. Yes, object-based, okay.
Okay, I'm sorry. I saw you walking around, but I wasn't sure whether it was because of me. Okay, so maybe I go ahead. So, okay, so this is the Conrad 3D. Now you should see the Conrad 3D slide.
Yes.
Right. So the Conrad 3D, as I said, is an object-based nowcasting of convective cells. We detect cells, analyze cells, track the cells, nowcast the cells. We have a Kalman filter model to smooth the tracks and to provide uncertainty information for the forecast locations. Yes, right. And the basic data we're using is radar reflectivity data, but there's also lightning data used, hydrometeor classification information used, and yeah, basically. But radar data is the main data source for this. Now, this scheme is operational at DWD since April 2023, this year. So I'm very happy about this because I personally spent a lot of work in developing Conrad 3D. And
did you move the slide, or are you still in the? Sorry to interrupt. We are still seeing the object-based ensemble nowcasting. Now we see something. Good. Sorry.
Really? I have no idea why it's lagging, so extremely lagging. I don't know. Maybe because of the animations. I don't know. So now I'm on object-based nowcasting of convective cells with the Conrad 3D EPS. Do you see the EPS slide? Very good. Okay, so Conrad 3D EPS is an ensemble-based method using Conrad 3D as a basis. So we have an ensemble prediction system based on Conrad 3D, in which not only the cell locations are nowcasted, but also cell attributes like the cell area and the cell severity we're trying to predict by incorporating life cycle analysis and artificial intelligence approaches. So the whole thing is based on a climatology by Wappler et al., who has analyzed, for example, as we see here in this picture, the relation of, for example, the cell age and the cell size. So here we see the median cell size as a function of cell age for different lifetime classes, which are these colors. And what we have discovered, or what they have discovered in their paper, is that you have some parabolic behavior, some parabolic model here. Of course, if you look at particular cases, you see huge deviations for the individual cases, but on average, you see such a parabolic structure.
So sorry, Manuel, are you at the slide 16?
No, I'm on 17. No way, it's not working. What happens if I leave the full screen mode? Maybe I should turn off my camera. Maybe this is also an option.
So we are seeing slide 16 at the moment.
16 and in full screen mode, right?
Yes.
Okay, because I left the full screen mode. Huh. This is strange.
Yeah, it didn't happen before, but never know with these systems. Maybe you try to go out and restart.
You mean leave the video conference?
No, not leave the application. Just.
Okay, I can just
unshare and then share again.
Yeah. I just close my presentation once. Maybe also that helps. Just a second. So I go back. Reopen, then I stop sharing.
Okay.
Just a second, please. So then I go to slide 16, 17. And then I start sharing again. Maybe I take that one. Maybe that is better. I shared my whole screen. Now I try to share only the presentation.
Okay, black screen at the moment.
A black screen, right? Ah. Yeah. Still black?
Do we have some? See, still black, yes.
Yeah, maybe sharing only the presentation. So I take that one again.
Yes, now we see 17, but not in presentation mode. Yeah, maybe you can keep it like this. I think it's okay. Now it's in presentation mode 17.
Okay.
Slide 17, so yes.
Maybe. Okay, I try, and you shout if it's not working again. Okay, so I was talking about the climatology by Wapler et al. And about these parabolic models for the cell sizes depending on the cell age, and we try to incorporate this parabola model to put it into an ensemble-Kalman filter in order to predict cell area, for example. So now, are you on the next slide?
Yes.
You see this animation?
Not the animation. We see something static. A good case.
Yeah, okay. So usually you should see here the animation of the ensemble-Kalman filter predicting the cell area. In this picture, you see the red lines are the predictions by the ensemble-Kalman filter, and at the beginning there's rather great fluctuation or uncertainty, and after some time then the model really predicts well the cell area. And so if you can't see it, maybe we should just go ahead. So there's no animation anymore. I'm on slide 19 now.
Yes.
You are too? Okay. So on the basis of this object-based ensemble nowcasting, we are also trying to combine this with the numerical weather prediction model. But how can you do this? Because usually the NWP only produces, doesn't produce any objects. So, however, on the left-hand side, you see again the measured radar data. You see the Conrad 3D EPS on the right.
Yeah, I think,
slide 20.
Sorry. No, sorry, because I think it's delayed a little bit. Now we are on slide 20, yes. Okay.
Unfortunately, I cannot see what you see, so yes. And on the right-hand side, there's the NWP. We have this NWP rapid update cycle ensemble, and we have the M4Rado forward operator that produces simulated radar data for all the ensembles in the NWP ensemble in steps of 5 minutes up to a forecast time of 12 hours. These are just reflectivity fields. But then we can take our Conrad 3D method, our cell detection method, and apply it to the simulated radar reflectivity by the model. And then we obtain a lot of cells, NWP cells. So we finally end up with an ensemble of cells from the model, and on the left-hand side, we have an ensemble of cells by the nowcasting. And this is also one important activity in Symphony, to combine these two ensembles of objects into a combined product called Conrad 3D Symphony. Yeah, so of course you need some algorithm to combine, you need some information reduction out of the huge amount of cells. What you can do is, for example, I'm on slide 21.
20.
Okay, so I just wait a couple of seconds to show you some probability of occurrence plots.
Still 20. Okay, yes, 21.
Okay, it's really very slow. So you see, the probability of occurrence, for example, of the exceedance of certain severity levels of the cells. Severity 0, severity 1, 2, 3. So the severity rating is done by the Conrad 3D method, depending on typical storm cell attributes like the cell-based wheel and other things. So this is one possibility for a product. And now I go to the next slide, which is about another product called the pseudo-member product.
We don't see it yet.
Yeah. Yeah, I mean, I don't want to torture you. I can skip some slides at the end, so we won't sit here until 8 o'clock, I think.
Still 21.
Oh, it's really unfortunate. Still 21, right? Ah.
Yes.
So I left the full screen.
Yeah, not moving.
Okay, then
yeah, 22. Okay,
oh,
yes.
No.
no, yes, you were.
Oh, that's not so funny, but what can we do?
Okay, 22, yes, in normal, not full screen mode. I think you can keep in this. Okay, fine, 22.
Yeah, okay. Yeah, so another product in this direction is a so-called pseudo-member product. So this is something in which we select cells out of the two ensembles, NWP and nowcasting, cells that locally well represent the cells in the vicinity to boil down the information, to reduce the information, right? This is also something that can be done. This is also something we have developed and which is being evaluated currently by our forecasters. So maybe I should I try it like this, and maybe I show you. Maybe I hop to this. Can you see slide 26?
Yes.
Okay. So let me show you at least some of the verification plots to show you that we are on the right track. So this is a plot that the modelers really like. It shows you a verification of reflectivities from the steps DWD nowcasting and reflectivities by Symphony rapid update cycle compared with the measured reflectivities for 1 month in 2022. So there's the fraction skill score on the y-axis and the lead time on the x-axis. And the red lines, let's look at the red lines. The red lines refer to the output reflectivities from the Symphony rapid update cycle from the model. And this is a plot our modelers really like, because the upper plot is the fraction scale score for really the ICANN D2 or ICANN RUC. And the lower red line refers to a verification with the Cosmo model, with the operational model we are running at the moment, without the rapid update cycle. And you see a huge difference in the scores between the two red lines, which reflects the progress they have made within 4 years of NWP development. You have to be careful, because the lower red line does not refer to the same verification period, but it's a huge gap, actually. Yeah, so for the fraction skill score here, the box size is rather large, 35 kilometers. So it's really a large scale analysis. And we have applied a threshold of 25 dB set here. So now I try to go to the next slide.
Yes.
Okay. So this is a verification of the steps nowcasting and the Symphony RUC and intense reflectivities. So intense was the combined grid-based method with the measured reflectivities in June 22. So you see the blue lines refer to the intense ensemble, to the combined ensemble, and the red line refers to the model. The black line refers to steps DWD, and you see a confirmation that really the combined method lies above the two other, and this shows us that we're on the right track, that it works. Yeah. Okay. I don't want to torture you too much today, so let's sum up a bit. Yeah, I want to say that we have some first promising prototypes for the combination of nowcasting and NWP algorithms. We have these steps, DWD method, the intense method, and the Conrad suite. We're running this in an online mode. We're evaluating this. There's an ongoing co-design process with our users, DWD forecasters, and also with the external customers. And we are also cooperating with a couple of other universities and projects. And for example, the nowcasting, the Symphony products are evaluated within the SSL testbed, which is also very important for us to assess the quality of everything. So this is the Symphony, a part of the Symphony group. I hope you're seeing this. So right in the middle, there should be Uli Blahak laughing into the camera. So Uli is our mastermind. And with this picture, I would like to thank you very much for your attention. And I'm sorry for the technical issues.
Yeah, thanks a lot, Manuel. I think, sorry for the technical issues. Do we have questions or comments for Manuel? Maybe I have a curiosity. Why you simulate a kind of reflectivity? Why not Doppler velocities?
Yeah, we could also consider Doppler velocity, but we just started with the reflectivity for the sake of simplicity. It's complicated enough to combine. So the model basically is the forward operator is, I think it is able to also simulate the Doppler velocity, and they are also working on forward operators for the dual pole quantities. So, but this is still future work, I would say.
Okay. Okay, I think we can call it a day. And okay, I would like to thank you again, all the speakers, for the international sessions. And I think we have just some communication from Miriam for the social dinner. So thank you also for the audience, online audience.
Thank you very much.
And thanks again, Manuel.
Bye-bye.
Grazie. Grazie Alessandro. Thank you, Dusan, for the lesson, the presentation, and just okay, I have to thank you, Manuel, Werner, all the speakers. Thank you again. Just a communication. Okay. for a very small communication. Ah no, in italiano. Grazie, scusa. Sorry, scusate, ho switchato. Va bene, grazie a tutti, grazie. Volevo solo comunicare per la cena di stasera la posizione, quindi una cosa molto semplice, dove si trova, adesso vediamo un po'. Sono un po'... sto anche pure io. Allora, giusto per indicare, questa è Piazza Maggiore, quindi ci troviamo Padevino San Daniele in via Altabella a 3/A alle 8:30. Giusto per indicare, questa è Piazza Maggiore, quindi pieno centro. Qui ci sono le due torri, qui c'è il mercato alle spalle, giusto per dire i punti più interessanti se uno passeggia. Piazza Santo Stefano. Volevo solo indicare che appunto si trova proprio vicinissimo alla piazza. Inoltre volevo dire che vabbè, in Piazza Maggiore c'è il cinema all'aperto che è gratuito e tutta l'estate c'è, quindi insomma se uno dopo vuole vedere una parte di film la può vedere. E tra l'altro c'è la festa di strada in via d'Azeglio, che è una strada che è una delle strade che si dipana dalla piazza e va verso fuori, e quindi di solito quando c'è la festa di strada ci dovrebbero essere musica, bancarelle, adesso non lo so, quindi può essere carino. La prima parte è pedonale sempre, la seconda parte è pedonale solo stasera perché c'è la festa della strada. Quindi niente, volevo dire solo questo, ci vediamo alle 8:30. Se qualcuno ancora non... 8:30, sì. E se qualcuno ancora non vuole partecipare, non ce l'ha detto, può aggiungersi e può dirlo. Basta, tutto qua. Per il resto, grazie di tutto, grazie Alessandro e ci vediamo domani. Ah già, è vero, vengo. Scusate, sono provata. Quest'ultima presentazione che non andava mi ha
segnato.